Between November 4th and November 9th, 2025, something extraordinary happened above our heads. While most of humanity went about their daily routines, completely unaware, our star unleashed one of the most intense barrages of electromagnetic fury witnessed in months. Multiple X-class solar flares erupted from active region AR4274, a sunspot complex so magnetically twisted that scientists watched it with a mixture of fascination and concern. These weren't gentle releases of energy, these were cosmic screams, each one carrying enough power to ionize Earth's entire upper atmosphere within minutes of the light reaching us. The numbers tell a story that should make anyone pause. An X-1.8 class flare peaked at 12:34 Universal Time on November 4th. Less than 12 hours later, another monster erupted, an X-1.1. Then came the M-class flares, the slightly smaller siblings that still pack enough punch to disrupt radio communications across entire hemispheres. An M7.4, an M8.6, each one launching coronal mass ejections toward Earth like electromagnetic cannonballs fired from 93 million miles away. If you're watching this, I need you to do something for me right now. Hit that like button and subscribe to this channel, because what we're about to discuss over the next 2 hours will challenge everything you think you know about the connections between space weather and events here on Earth. And tell me in the comments, where are you listening from, what time is it there right now, and did you see any auroras during these recent storms? I'm genuinely curious about your experiences. Now, here's where it gets interesting. These coronal mass ejections didn't just launch into space randomly. They were aimed directly at us. The first major CME, the one associated with that M7.4 flare, left the Sun at approximately 22:53 Universal Time on November 4th. NASA's models calculated its velocity between 1100 and 1400 kilometers per second. Think about that for a moment. A cloud of superheated plasma larger than Jupiter, racing toward Earth at nearly 1% the speed of light. When that first CME slammed into Earth's magnetosphere at 5:17 Universal Time on November the 7th, the impact was instantaneous and dramatic. Solar wind speeds, which normally hover around 400 kilometers per second, suddenly surged past 800 kilometers per second. Some monitoring stations recorded peaks of 850 kilometers per second. The interplanetary magnetic field strength jumped from weak background levels below 7 nanoteslas to a robust 13 nanoteslas, but it was the orientation of that magnetic field that mattered most. The BIS component, the north-south orientation of the interplanetary magnetic field, started fluctuating wildly between northward and southward orientations. When it pointed southward, dropping to negative 14 nanoteslas at 21:30 Universal Time, it created what space physicists call favourable conditions for magnetic reconnection. Earth's magnetic field lines, normally closed and protective, suddenly opened up. Charged particles from the solar wind poured in, following those field lines down to the upper atmosphere where they collided with oxygen and nitrogen molecules, releasing the ethereal glow we call auroras. The geomagnetic response was swift and powerful. Within hours, Earth's magnetic field fluctuated between quiet and active conditions, then crossed the threshold into G1 minor geomagnetic storm territory at 21 Universal Time on November 5th. But that was just the beginning. By 22:53 Universal Time, the storm intensified to G2 moderate levels, and by 5:36 Universal Time on November 6th, we hit G3 strong geomagnetic storm conditions. 22 states across the United States had aurora visibility that week. From Alaska down to Illinois, the night sky danced with colours that most people in those latitudes never expected to see. Not just the typical green curtains of oxygen emission at lower altitudes, but the deep reds and purples of high-altitude oxygen and nitrogen ionization. Social media exploded with photos and videos, people standing in fields and backyards, watching in awe as the cosmic light show unfolded overhead. But something else was happening that most people didn't notice. The National Oceanic and Atmospheric Administration issued watches and warnings, not just for pretty lights, but for real technological threats. G3 storms are capable of causing voltage fluctuations in power systems. They increase the drag on low Earth orbit satellites, potentially degrading their orbits. They cause intermittent high-frequency radio degradation at high latitudes. GPS systems start reporting larger than normal errors. The modern technological infrastructure we depend on every single day becomes vulnerable. And here's what really matters. What should send a chill down your spine? This wasn't just one storm. Multiple coronal mass ejections left the Sun in quick succession. A full halo CME departed at approximately 22:23 Universal Time on November 5th, associated with that M8.6 flare. Another CME was predicted to deliver a glancing blow on November 8th. The Space Weather Prediction Center warned that disturbed space weather would continue through November 10th. We weren't dealing with a single event. We were dealing with a sustained bombardment. Active region AR4274 remained large and magnetically complex as it rotated to face Earth more directly. The probability forecasts were ominous. 70% chance of additional M-class flares, 25% chance of more X-class eruptions. Each new flare could launch another CME in our direction. Each new CME could trigger another round of geomagnetic storms. The pattern suggested we were in for an extended period of solar chaos. Now, conventional wisdom tells us that solar storms are fascinating, but ultimately harmless to people on the ground. The atmosphere protects us from the radiation. The magnetic field deflects most of the particles. We might lose some satellite communications or see some power grid fluctuations, but nothing truly catastrophic. That's the story we're told. That's what the official channels emphasize whenever these events occur. But what if there's more to this story? What if these electromagnetic disturbances reaching Earth's surface have effects that mainstream science is only beginning to understand, or perhaps reluctant to fully acknowledge? What if the timing of these particular solar storms, happening right now in early November 2025, connects to other phenomena in ways that seem too precise to be coincidental? The auroras that painted the sky weren't just pretty lights. They were visible manifestations of enormous energy transfer from the solar wind into Earth's magnetosphere and down into the ionosphere. That energy doesn't just disappear after creating those beautiful displays. It propagates through the Earth's electromagnetic environment. It induces currents in long conductors like power lines and pipelines. It creates fluctuations in the global electric circuit that connects the ionosphere to the Earth's surface. Scientists have known for decades that geomagnetic storms can induce what are called telluric currents, electric currents that flow through the Earth's crust. These aren't weak, insignificant currents. During major geomagnetic storms, these currents can be strong enough to corrode underground pipelines, overwhelm electrical ground systems, and interfere with the railway signalling. The ground beneath our feet literally becomes electrified during these events. But could these electromagnetic disturbances reach even deeper? Could they interact with geological processes in ways we're only now beginning to measure and understand? The timing of what happened during this first week of November becomes crucial when you start connecting dots that most people never think to connect. Consider the solar wind velocity, 850 kilometers per second. That's not just fast, it's extraordinarily fast even by solar storm standards. When solar wind at those velocities impacts Earth's magnetosphere, the compression on the day side is dramatic. The magnetosphere, which normally extends about 10 Earth radii into space on the sun-facing side, can compress down to 6 Earth radii or less. That compression translates to pressure, real physical pressure exerted on the entire electromagnetic envelope surrounding our planet. And here's something that should make you pause and think. Multiple independent research teams have recently published findings suggesting correlations between geomagnetic, storm intensity and seismic activity. Not immediate cause and effect, but delayed correlations. Time lags measured in specific intervals. The mechanisms proposed involve everything from magnetostriction effects in crustal rocks to electromagnetic induction altering fluid dynamics in fault zones. The week of November 4th through 9th wasn't just any week of solar activity. It was a precisely timed convergence of multiple factors. The intensity of the storms, the sustained nature of the bombardment, the particular orientation of the interplanetary magnetic field, allowing maximum energy coupling, and perhaps most intriguingly, what else was happening in the solar system during this exact same time frame? Because while Earth was being battered by this electromagnetic onslaught from our star, two very unusual objects were making their way through the inner solar system. Objects that shouldn't be where they are. Objects behaving in ways that defy conventional explanations. Objects whose presence during this period of intense solar activity might not be coincidental at all. The sun had screamed at Earth with unprecedented fury during this first week of November. But to truly understand the significance of what happened, we need to dig deeper into the specific characteristics of these storms and why they stood out even among the chaos of solar maximum activity. Let's talk about active region AR4274 for a moment. This wasn't just another sunspot group rotating across the solar disk. This was a magnetically complex monster that solar physicists had been tracking with increasing concern. The region exhibited what's called a beta-gamma delta magnetic configuration, which is essentially the most unstable arrangement of magnetic fields you can find on the Sun's surface. Imagine trying to hold two powerful magnets together with the same poles facing each other. The tension, the instability, the inevitable violent release when the field lines finally snap and reconnect. That's what was brewing in AR4274. When the first X-class flare erupted on November 4th, instruments on NASA's Solar Dynamics Observatory captured the explosion in multiple wavelengths of extreme ultraviolet light. The footage shows something that looks almost alive, almost intentional. Bright loops of superheated plasma glowing at temperatures exceeding 10 million degrees Celsius, suddenly erupting from the Sun's surface. These loops, following the twisted magnetic field lines, stretched hundreds of thousands of kilometers into space before snapping and releasing their energy in a flash that momentarily outshone the entire solar disk. The timing of these eruptions follows patterns that solar physicists are still trying to fully understand. Active regions don't just randomly produce flares. There's a build-up phase as magnetic energy accumulates, a triggering mechanism that we still don't completely comprehend, and then the explosive release. What makes AR4274 particularly fascinating is how it produced multiple major flares in such rapid succession. It's as if once the first magnetic structure destabilized, it triggered a cascade effect through the entire region. Each coronal mass ejection that left the Sun carried not just plasma and magnetic field, but information. The structure of the CME, the way its magnetic field is oriented, the density and temperature of the plasma, all of these factors tell us something about the conditions in the corona at the moment of eruption. The full halo CME that departed on November 5th was particularly interesting because of its symmetry. When you see a perfectly circular halo in coronagraph images, it means the eruption was aimed almost directly at the observer. In this case, that observer was Earth. The journey from Sun to Earth took approximately 2 days for these CMEs. During that time, they ploughed through the ambient solar wind, creating what space physicists call a shock front ahead of the main plasma cloud. This shock front is where particles get accelerated to extremely high energies. When it reached Earth's magnetosphere, the impact was recorded by satellites positioned at the L1 Lagrange point, about 1.5 million kilometers upstream from Earth. These spacecraft serve as our early warning system, giving us anywhere from 15 to 60 minutes of notice before the disturbance reaches our planet. But here's something most people don't realize about geomagnetic storms. The energy that creates those beautiful auroras doesn't just stay in the upper atmosphere. The aurora oval, that ring of light surrounding each magnetic pole, is actually the visible signature of millions of amperes of electric current flowing through the ionosphere. These currents, called auroral electrojets, create their own magnetic fields that can be measured on the ground. And these ground magnetic field variations, in turn, induce electric fields in any conductor they encounter. The power grids of high-latitude nations experienced this firsthand during the storms. In regions like Scandinavia and northern Canada, utility companies have sophisticated monitoring systems that track geomagnetically induced currents in real time. During the peak of the November 7th storm, some transformer stations recorded current variations large enough to trigger protective systems. The grids didn't fail, but they came closer to instability than most people realized. Now think about this from a broader perspective. We're not just talking about technological systems being affected. We're talking about the entire electromagnetic environment of Earth being fundamentally altered for days at a time. The ionosphere, that layer of charged particles between 80 and 600 kilometers altitude, normally acts like a mirror for certain radio frequencies. During geomagnetic storms, that mirror becomes distorted, warped by the influx of particles and energy from the magnetosphere. High-frequency radio waves that normally bounce predictably off the ionosphere suddenly scatter in random directions, or get absorbed entirely. GPS satellites broadcast their signals through this disturbed ionosphere, and the changing density of charged particles delays those signals by varying amounts. Your phone or car navigation system tries to calculate your position based on the precise timing of signals from multiple satellites. But during a geomagnetic storm, those timing calculations become progressively less accurate. Errors that are normally measured in meters can grow to tens of meters or more. Aviation is affected too. Polar routes, the great circle paths that connect North America with Asia, pass through regions where high-frequency radio communication becomes unreliable or impossible during strong geomagnetic storms. Airlines have contingency plans to reroute flights to lower latitudes where communication remains possible, but these diversions burn extra fuel and add flight time. The radiation environment in space becomes dramatically more dangerous during solar storms. Satellites in geosynchronous orbit, 35,000 kilometers above the equator, suddenly find themselves exposed to much higher fluxes of energetic particles. These particles can penetrate electronics, causing bit flips in computer memory, degrading solar panels and over time shortening the operational lifetime of expensive spacecraft. And then there's the phenomenon that scientists are only beginning to fully characterize: the coupling between space weather and the neutral atmosphere below. It turns out that energy deposited in the upper atmosphere during geomagnetic storms doesn't just stay there. It affects atmospheric chemistry, particularly the production and destruction of various nitrogen and oxygen compounds. These changes propagate downward over time, potentially influencing atmospheric circulation patterns and even surface weather on seasonal timescales. But perhaps most intriguing are the biological effects. Multiple studies over the years have documented correlations between geomagnetic activity and various physiological parameters: increased rates of heart attacks and strokes during and after major storms, changes in human reaction times and cognitive performance, alterations in sleep patterns and mood. The mechanisms aren't fully understood, but they likely involve the disruption of biological magnetoreception systems that many organisms, including humans, appear to possess at some level. Migratory birds become disoriented during geomagnetic storms because they use Earth's magnetic field for navigation. Whales and dolphins, which also rely on magnetic sensing for long-distance navigation, have been observed beaching more frequently during periods of disturbed geomagnetic activity. If these animals, with their exquisitely sensitive biological magnetometers, can be so profoundly affected by space weather, why should we assume humans are completely immune? The week of November 4th through 9th represented one of those rare windows when space weather moved from the realm of academic interest into something that touched nearly every technological system we depend on. The auroras that captivated millions of observers were beautiful, yes, but they were also warnings. Visible manifestations of invisible forces that were reshaping the electromagnetic environment of our entire planet. And here's what should really make you stop and think. This bombardment from the sun wasn't happening in isolation. It was happening at a very specific moment in time, a moment when other extraordinary events were unfolding elsewhere in the solar system. Events involving objects that have captured the attention of astronomers and conspiracy theorists alike. Events that, when viewed together with these solar storms, create a pattern that seems almost too perfect, too precisely timed to be purely coincidental. The question we need to ask ourselves is, what was the sun trying to tell us with this unprecedented fury during the first week of November 2025? Or perhaps more disturbingly, what was it responding to? What cosmic choreography was playing out across our solar system, with Earth and its magnetic field caught right in the middle of forces we're only beginning to comprehend? The earthquake connection, scientists don't want you to know. On November 3rd, 2025, at precisely 29 minutes past midnight, Afghanistan time, the ground beneath Balkh province began to shake. A magnitude 6.3 earthquake struck at a depth of 28 kilometers, a moderately shallow event that released energy equivalent to thousands of tons of explosives. 30 people died, 956 were injured, homes collapsed across 2 provinces. But here's what most news reports didn't tell you, what most seismologists won't discuss publicly. This earthquake happened exactly 27 days after a major geomagnetic storm. 27 days. Hold that number in your mind. In March 2025, a team of researchers published a groundbreaking study in Geophysical Research Letters. The paper, titled On Solar Terrestrial Interactions, Correlation Between Intense Geomagnetic Storms and Global Strong Earthquakes, analysed nearly a century of data. They introduced a new statistical method called shift neighbourhood matching correlation, and what they found should have made headlines everywhere. It didn't. The research revealed an increased likelihood of earthquakes following geomagnetic storms, particularly at a time lag of 27 to 28 days. Not immediately, not randomly, but consistently, at this specific interval. The correlation was statistically significant, with a probability of being random less than 1 in 100,000. Think about that. Less than 0.001% chance this pattern is coincidence. But, wait, you might be thinking. Scientists have been arguing about solar earthquake connections for over a century and a half. This goes all the way back to 1853, when Rudolf Wolf, the great solar astronomer, first proposed that sunspots might influence earthquake occurrence. Since then, countless studies have claimed correlations, while other studies have found nothing. The United States Geological Survey's official position remains that there is no convincing evidence that space weather causes earthquakes. So why should we believe this new research is any different? Here's why. Previous studies looked at immediate correlations or very short time delays. They searched for earthquakes happening during solar maximum versus solar minimum. They tried to find patterns in days or weeks. But they missed the sweet spot. They missed that specific 27 to 28 day window where the correlation becomes undeniable. The mechanism proposed in the March 2025 study involves something called the reverse piezoelectric effect. You're probably familiar with the regular piezoelectric effect, how compressing certain crystals like quartz generates an electrical voltage. Quartz is everywhere in Earth's crust. It's one of the most abundant minerals. The reverse piezoelectric effect works the opposite way. Apply an electric field to quartz-bearing rocks, and they physically deform, they change shape, they generate stress. Now imagine what happens when a geomagnetic storm induces powerful electric currents in Earth's crust. These telluric currents, as they're called, flow through rocks that contain vast amounts of quartz. The reverse piezoelectric effect causes those rocks to deform slightly. In most places, this deformation is insignificant, too small to matter. But in fault zones that are already stressed, already near their breaking point, already primed to rupture, that tiny additional stress could be the trigger. The final straw that breaks the tectonic camel's back. But there's another mechanism that some researchers find even more compelling. A July 2020 study published in Scientific Reports analysed 20 years of data from NASA and ESA's Solar and Heliospheric Observatory satellite. The team compared proton density and velocity measurements from the solar wind with the worldwide seismicity catalogue. They found clear correlation between proton density peaks and the occurrence of large earthquakes with a magnitude greater than 5.6, with a time shift of 1 day. 1 day for immediate effects from proton bombardment, 27 to 28 days for the delayed effects from geomagnetic storms. 2 different mechanisms, 2 different timescales, both pointing to the same uncomfortable conclusion. The Sun influences earthquake activity on Earth. The proton density mechanism works like this. When Earth passes through a high-density region of the solar wind, the flux of charged particles penetrating into the upper atmosphere increases dramatically. These particles create electrical disturbances that propagate downward through the global electric circuit. At the surface, these disturbances induce currents in the ground. Once again, the reverse piezoelectric effect comes into play, but this time the response is much faster because the electrical disturbances reach peak intensity within hours of the solar wind change. Now let's get back to that Afghanistan earthquake on November 3rd. Work backward 27 days, and you arrive at October 7th. What was happening with space weather on October 7th? The records show elevated geomagnetic activity. Not a major storm, but definitely disturbed conditions. The kind of conditions that would have induced substantial telluric currents in Earth's crust. The kind of conditions that, according to the new research, would prime fault zones for rupture approximately 4 weeks later. But Afghanistan wasn't alone. On February 8, 2025, a magnitude 7.6 earthquake struck the Cayman Islands at a depth of 17 kilometers. 39 days after a coronal mass ejection impacted Earth on January 1st, which itself hit Earth on January 4th, after erupting from the Sun on January 1st. 39 days falls outside that 27 to 28 day window. But remember, these are statistical correlations, not rigid mechanical relationships. The delays can vary somewhat depending on local geological conditions, the specific characteristics of the fault zone, and the intensity of the geomagnetic disturbance. Then, on March 28, 2025, Myanmar experienced a magnitude 7.7 earthquake. Again, when you work backward through the geomagnetic storm records, you find elevated activity at the right time interval. The pattern repeats, the correlation holds. A 2012 study published in the journal Natural Hazards examined earthquakes in the Vrancia zone of Romania and found that 68% of major earthquakes occurred within a few days of geomagnetic storms. A different study looking at Italian earthquakes over more than a century found an 11-year modulation in seismicity that matched the solar cycle. The earthquakes clustered near solar maximum when geomagnetic storms are most frequent. Research from Japan published in March 2025 went even deeper, proposing that solar heat, not just magnetic storms, plays a role in earthquake activity by altering surface temperatures and underground pressure. This builds on their 2022 study that found connections between sunspot activity and seismic patterns. The idea is that temperature changes driven by variations in solar radiation affect rock properties and underground water movement. Over seasonal and yearly timescales, these thermal effects could influence the stress state of fault zones. So we have multiple independent mechanisms all pointing in the same direction. Fast-acting effects from solar proton density changes, delayed effects from geomagnetic storm-induced telluric currents, longer-term effects from solar radiation variations. Each mechanism operates on a different timescale, but they all connect solar activity to seismic activity. The mainstream scientific establishment has been slow to accept these findings. The USGS page on this topic is still titled, "Do solar flares or magnetic storms cause earthquakes?" with the answer being a firm no. They point out that earthquakes show no 11-year periodicity matching the solar cycle. They emphasize that earthquakes are driven by processes in Earth's interior and would occur even if solar activity ceased. Both statements are technically true but miss the point entirely. Nobody is claiming the sun causes earthquakes. The sun doesn't create the tectonic stress that ultimately leads to rupture. That stress comes from plate tectonics, from the slow grinding movement of lithospheric plates driven by convection in the mantle. But triggering is different from causing. A fault that's already stressed to 99% of its breaking strength doesn't need much to push it over the edge. A small additional stress, applied at just the right time, in just the right location, can be enough. Think of it like a rock slide waiting to happen on a steep mountain slope. The rocks are already unstable, already held in place by friction that's barely adequate. You don't need a massive force to start the slide. A small vibration, a minor disturbance, even a loud sound in some cases, can be sufficient to overcome that last bit of friction and send tons of rock tumbling down the mountainside. Did the sound cause the rock slide? No, gravity and erosion caused it, but the sound triggered it. That's the relationship between solar storms and earthquakes. The sun doesn't cause the tectonic stress, but it can provide the trigger for faults that are already primed to fail. And if that trigger operates on a predictable timescale, if geomagnetic storms consistently increase earthquake probability 27 to 28 days later, then we have something incredibly valuable. We have a potential forecasting tool. Imagine if we could say, with confidence, that following a major geomagnetic storm, certain seismically active regions face elevated earthquake risk during a specific time window 4 weeks later. Emergency services could be on higher alert. Critical infrastructure could be inspected and reinforced. People could be educated about emergency preparedness. We can't predict exactly when or where an earthquake will strike, but we might be able to identify periods of heightened risk. Of course, there's fierce resistance to this idea. Part of it is legitimate scientific caution. The mechanisms aren't fully proven. The correlations, while statistically significant, don't predict every earthquake. There are false positives when geomagnetic storms occur, but no major earthquakes follow. There are false negatives when large earthquakes happen without any preceding solar activity. The relationship is probabilistic, not deterministic, which makes some scientists uncomfortable. But there's also institutional inertia and, dare I say it, professional pride at stake. Seismology and space physics are separate disciplines with separate journals, separate conferences, separate funding streams. Researchers who suggest solar-terrestrial interactions affecting earthquakes often find their work dismissed by earthquake specialists who view it as fringe science. Meanwhile, space physicists aren't particularly interested in earthquakes because it's outside their domain, so this crucial area of research falls into a gap between disciplines. And then there's the question of what it means if the connection is real. If solar storms, which we can monitor and to some degree predict, influence earthquake timing, then the implications are staggering. It means Earth's interior is far more coupled to space weather than we ever imagined. It means the solid ground beneath our feet responds to invisible electromagnetic forces from the sun. It means our planet is less isolated, less independent, more connected to the broader solar system environment than conventional geology acknowledges. Now remember those intense geomagnetic storms that battered Earth during the first week of November, the G3 level disturbances, the sustained bombardment over multiple days, the powerful induced currents in the ground. If the 27 to 28 day correlation holds, if the mechanism is real, then we should be watching seismic activity very carefully during the first week of December, particularly in regions with major fault zones that are known to be under high tectonic stress. What happens if a significant earthquake strikes during that predicted window? What happens if the pattern holds once again, adding one more data point to a correlation that's already statistically overwhelming? At what point does the scientific community have to acknowledge that something real is happening here? That the sun and the solid Earth are connected in ways that textbooks don't yet describe? And here's the truly unsettling thought. Those solar storms in early November weren't random events. They coincided with other phenomena, other objects moving through our solar system in ways that defy easy explanation. Could there be an even deeper connection? Could the forces at play be more complex, more interconnected, more precisely orchestrated than even the most groundbreaking research has yet revealed? 3I-ATLAS lost its tail and gained an engine. On November the 5th, 2025, two astronomical observatories released new images of 3I-ATLAS taken just days after its perihelion passage. The Arnaves Observatory in Spain and the Virtual Telescope project both captured the interstellar visitor at a distance of 1.38 astronomical units from the Sun. Scientists and amateur astronomers eagerly downloaded the images, expecting to see the spectacular display that should have been there. What they saw instead was deeply disturbing. 3I-ATLAS appeared as a compact ball of light surrounded by a faint glow. There was no clear cometary tail, no massive plume of dust and gas streaming away from the sun, no evidence of the violent outgassing that should have been occurring after the object had just been subjected to intense solar heating at perihelion. The coma looked remarkably similar to how it appeared in Hubble Space Telescope images from July 21st, months earlier, when the object was still far from the sun. This was wrong. This violated everything we know about how comets behave. To understand why this is so problematic, you need to grasp what perihelion means for a comet. 3I-ATLAS reached its closest point to the Sun on October 29th, coming within 203 million kilometers, or 1.36 astronomical units. At that distance, the solar radiation delivers 770 watts of power per square meter of the comet's surface. For an object estimated to be at least 5 kilometers in diameter, that's tens of gigawatts of total solar energy being absorbed. Comets are fundamentally dirty snowballs, mixtures of water ice, frozen carbon dioxide, frozen methane, dust, and rocky material left over from the formation of a planetary system billions of years ago. When a comet approaches the Sun, that ice begins to sublimate, turning directly from solid to gas without passing through a liquid phase. The gas expands rapidly, carrying dust particles with it, creating the glowing coma and tail that define a comet's appearance. The closer to the Sun, the more intense this process becomes. By the time a comet reaches perihelion, it should be experiencing maximum outgassing. The surface temperature soars, volatile materials deep within the nucleus heat up and explosively vent into space. The tail should grow longer, brighter, more spectacular. This is basic cometary physics, observed and documented for hundreds of comets over centuries of observation. 3I-ATLAS showed none of this. The November 5th images displayed an object that looked almost inert, quiet, controlled, as if the intense solar heating that should have been triggering massive outgassing was having minimal effect. But NASA's Jet Propulsion Laboratory had already reported something even more puzzling. 3I-ATLAS was exhibiting non-gravitational acceleration. The object was changing its velocity in ways that couldn't be explained by the sun's gravity alone. The reported acceleration, normalized at 1 astronomical unit from the sun, indicated that some force other than gravity was acting on the object. In normal comets, non-gravitational acceleration comes from the rocket effect of asymmetric outgassing. As jets of gas vent from the sunlit side of the nucleus, they create thrust, like tiny rocket engines. This thrust can slightly alter the comet's trajectory. The effect is well understood and routinely measured for solar system comets. But the magnitude of the non-gravitational acceleration correlates directly with the amount of outgassing. More gas ejected means more thrust, which means more acceleration. Here's the problem. Avi Loeb, the Harvard astrophysicist who's been tracking 3I-ATLAS since its discovery, did the calculations. Based on momentum conservation and the reported non-gravitational acceleration, he determined that 3I-ATLAS must have lost more than 10 to 20% of its initial mass during perihelion passage. For a comet 5 kilometers in diameter, that's an enormous amount of material. We're talking about cubic kilometers of ice and dust ejected into space. Where was it? Where was this massive debris cloud? Where was the dust tail that should have stretched for millions of kilometers? Where were the gas emissions that space telescopes should have been detecting with ease? The November 5th images showed nothing remotely consistent with losing 10 to 20% of total mass. The object appeared compact and relatively quiescent. The faint coma around it extended only a few 100,000 kilometers, far smaller than expected. There was no obvious tail pointing away from the sun, no broad fan of material being swept back by solar radiation pressure and the solar wind. Loeb compared the 3I-ATLAS images to images of Comet Lemon, a regular solar system comet, taken on November 3rd by the same Arnaves Observatory using the same telescope. Lemon displayed exactly what you'd expect. A clear, bright tail streaming away from the sun, obvious dust emissions, the textbook appearance of a comet near perihelion. The contrast was stark and undeniable. Now, there's a geometric caveat to consider. At the time of the November 5th observations, 3I-ATLAS was only 13 degrees away from the sun in Earth's sky. If the tail was pointing directly away from the sun, we'd be viewing it almost head-on, which makes it harder to detect. But this same geometry applied on July 21st, when Hubble imaged 3I-ATLAS at only 10 degrees from the sun. In that earlier image, Hubble clearly captured an anti-tail, an elongation pointing toward the sun rather than away from it. That anti-tail showed up just fine despite the unfavourable viewing angle. So why would a much larger, brighter dust tail fail to appear in November after perihelion? The anti-tail itself was anomalous. Most comets don't display prominent anti-tails, and when they do appear, they're usually optical illusions caused by perspective effects as Earth passes through the comet's orbital plane. But detailed analysis of the Hubble image showed that the 3I-ATLAS anti-tail wasn't an optical illusion. It represented real material, dust and gas, being ejected toward the sun. Material moving in the wrong direction. Over the coming weeks, as the angle between 3I-ATLAS and the sun increased from Earth's perspective, the viewing geometry would improve dramatically. By mid to late November, terrestrial observers would have a clear side view of the object. If a massive tail existed, if all that missing mass was out there forming a debris cloud, it would become visible. Astronomers waited with their telescopes ready. But the missing tail wasn't the only anomaly piling up around this object. On November 8th, Avi Loeb appeared on the cable news program Banfield and dropped another observation that sent ripples through the online astronomy community. He discussed what he called the non-gravitational acceleration in terms that made it sound less like outgassing and more like propulsion. He suggested that 3I-ATLAS might be revving an engine. An engine? Not random jets of sublimating ice, but controlled thrust. Deliberate acceleration. The language was careful, the speculation framed as hypothesis rather than conclusion, but the implication was clear. If you needed to explain the observed acceleration without the visible outgassing that should accompany it, one possibility was technological propulsion. Chemical rockets, the kind humans have been building for decades, achieve exhaust velocities of 3 to 5 kilometers per second. That's about 10 times faster than the maximum ejection speed of volatiles, sublimated from a cometary surface by sunlight. Ion thrusters, More advanced technology that we're only beginning to deploy on spacecraft reach exhaust velocities of 10 to 50 kilometers per second, up to 100 times faster than cometary outgassing. The difference matters because thrust equals mass flow rate times exhaust velocity. If you can eject material at higher velocity, you need less mass to produce the same thrust. A technological thruster could provide the observed non-gravitational acceleration while ejecting far less than 10 to 20% of the object's mass. Maybe just a few percent, maybe less. An amount that might not produce an obvious visible tail, especially if the exhaust was directed and controlled, rather than spraying randomly in all directions. This is where the conversation enters territory that makes conventional astronomers deeply uncomfortable. We're talking about applying engineering principles to an object from another star system. We're discussing thrust vectoring and propulsion systems in the context of what's officially classified as a comet. We're taking seriously the possibility that 3I-ATLAS might not be natural at all. The conservative response is to point out that comets are complex and sometimes behave in unexpected ways. Outgassing doesn't always produce obvious tails. Viewing geometry can hide structures that are actually present. The calculations about mass loss have uncertainties. We shouldn't jump to exotic explanations when conventional explanations, however strange, remain possible. But at what point do the conventional explanations become more implausible than the exotic ones? At what point does invoking special circumstances and unusual geometries and atypical behaviour become less satisfying than admitting we might be looking at something fundamentally different? The blue appearance that 3I-ATLAS displayed during perihelion adds another layer to this puzzle. When objects heat up, they typically glow in predictable ways determined by their temperature and composition. The blue coloration could come from ionized carbon monoxide emissions, which would be consistent with a natural comet rich in carbon compounds. But it could also come from something else, an artificial light source perhaps. Plasma from an engine exhaust. The blue of extreme temperatures generated by technological processes rather than passive solar heating. The problem is that we don't have enough data yet to definitively distinguish between these possibilities. The spectroscopic observations needed to identify specific molecules and determine their velocities require instruments operating at the limits of their capabilities. 3I-ATLAS is relatively faint, relatively far away, and moving through a region of sky where observations are challenging. NASA's James Webb Space Telescope has the sensitivity and spectral resolution needed to settle many of these questions, but Webb's observing schedule is packed with approved programs planned years in advance. Getting directors discretionary time for unexpected targets requires compelling justification. As November progressed, the angle between 3I-ATLAS and the Sun from Earth's perspective continued to increase. By November 11th, ground-based telescopes would have their first good opportunities to observe the object since before perihelion. What those observations revealed, or failed to reveal, would be crucial for understanding what we're actually dealing with. If a massive tail appeared, consistent with losing 10 to 20% of total mass, then maybe 3I-ATLAS was just an unusually quiet comet that happened to eject material in ways we didn't observe clearly. If no tail appeared, if the object remained compact and relatively quiescent despite the reported non-gravitational acceleration, then the technological hypothesis would gain significant support. Not proof, not yet, but support that would be increasingly difficult to dismiss. The propulsion question connects to something even more profound. If 3I-ATLAS possessed the ability to alter its trajectory, to perform what aerospace engineers call delta V maneuvers, then its current path through our solar system might not be accidental. The alignment of its orbit with the ecliptic plane, coming within less than 5 degrees of the plane where all the planets orbit, could be intentional rather than coincidental. The timing of its arrival, passing close to Mars and Venus and Jupiter at specific intervals, could be navigation rather than chance. And if 3I-ATLAS was navigating, if it was adjusting its course, using some form of propulsion system, then every assumption about its origin, its purpose and its nature would need to be reconsidered. We wouldn't be dealing with a passive chunk of ice and rock falling through space. We'd be dealing with something that made choices, something with agency, something that came here deliberately. The missing tail pointed toward possibilities that most scientists weren't ready to consider. But the evidence was piling up, observation by observation, anomaly by anomaly. each one harder to explain away than the last. 7 jets that shouldn't exist. At 4:10 Universal Time on the morning of November 8, 2025, 3 astronomers pointed their telescopes at 3I-ATLAS from their observatory location. M. Jager, G. Riemann, and E. Prosperi had been waiting for this opportunity, for the moment when the interstellar visitor would emerge from the sun's glare at a wide enough angle to permit detailed imaging. The object was 29 degrees away from the sun in the sky, 7 to 10 degrees above the horizon, with bright moonlight washing out fainter stars. Not ideal conditions, but workable. They captured 24 exposures through a green filter, each lasting 35 seconds, along with 2 exposures in red and 2 in blue. Then they stacked the images to reduce noise and enhance faint details. What emerged from that processing would become one of the most important astronomical images of 2025. 3I-ATLAS wasn't just sitting there quietly. It was surrounded by a complex structure of at least 7 distinct jets. 7 jets. Some pointing toward the sun, some pointing away, some angled in other directions entirely. The jets extended outward from a central bright core, creating a pattern that looked less like random outgassing and more like something organized, deliberate. The entire structure was enveloped in a large glowing halo that extended out to approximately 500,000 kilometers, or 5 arc-minutes on the sky. Let me explain why this is extraordinary. Cometary jets are common. We see them all the time. As sunlight heats the surface of a rotating cometary nucleus unevenly, certain areas become more active than others. Patches of ice exposed on the sunward side sublimate vigorously, creating narrow jets of gas and dust that spray into space. These jets create pressure, they push on the nucleus, and if they're not perfectly balanced, they cause that non-gravitational acceleration we've been discussing. But cometary jets usually display certain characteristics. They tend to point away from the sun because that's where the heating is strongest. They evolve over time as the nucleus rotates, different areas coming into and out of sunlight. They're generally consistent with the thermal environment the comet is experiencing. What they don't do is point in opposite directions simultaneously with equal vigor. 3I-ATLAS was showing jets going both toward and away from the sun at the same time. Multiple jets, all active, creating a symmetric or near-symmetric pattern around the nucleus. This configuration suggested that whatever was driving these jets wasn't simply solar heating of exposed ice patches. Something else was going on. Avi Loeb, analysing the November 8th images, pointed out a crucial calculation. If the non-gravitational acceleration of 3I-ATLAS came from these jets through normal cometary outgassing, and if the jets were spraying in multiple directions as observed, then the efficiency of thrust generation would be very low. Most of the ejected mass would be cancelling itself out, jets pushing in opposite directions, creating opposing forces. To produce the measured acceleration under these conditions, the object would need to have ejected much more than the 10 to 20% of initial mass calculated earlier, possibly a substantial fraction, maybe even most of its total mass. Think about what that means. If 3I-ATLAS was a natural comet that lost, say, 40 or 50% of its mass during perihelion passage, we should be looking at a massive debris cloud, an enormous diffuse structure of gas and dust expanding outward at kilometers per second, the kind of thing that would be impossible to miss, that would dominate the field of view in any image. But the November 8th images showed a relatively compact object. The 500,000 kilometer halo sounds large, but for a comet that's supposedly just explosively disintegrated, it's actually rather small and well-defined. Natural comets that undergo major fragmentation or mass loss events become spectacular in visible light. They develop huge comas and tails that can stretch for tens of millions of kilometers. Their brightness often increases dramatically as fresh ice is exposed and sublimates rapidly. They become naked eye objects, things that casual observers can spot without telescopes. 3I-ATLAS did none of this. It brightened somewhat during perihelion, yes, but remained a telescopic object, relatively faint, relatively compact. The alternative explanation shifts the framework entirely. What if the jets weren't passive outgassing driven by solar heat? What if they were active, controlled emission of material for propulsion purposes? Technological thrusters could produce jets in any direction desired, independent of where the sun was located. Multiple thrusters firing simultaneously could create complex patterns while delivering net thrust in a specific direction. And crucially, thrusters operating at high exhaust velocity would require far less propellant mass to achieve the same total impulse. This is basic rocket science, the kind of calculations aerospace engineers do routinely. The rocket equation tells us that the change in velocity, the delta V, depends on the exhaust velocity and the mass ratio. Higher exhaust velocity means you need less propellant mass to achieve the same maneuver. Chemical rockets are limited by the energy density of chemical reactions. Ion drives use electrical energy to accelerate ions to much higher velocities, dramatically improving efficiency. If 3I-ATLAS was using something comparable to ion propulsion, it could execute the observed trajectory changes while ejecting only a few % of its total mass. The jets we're seeing might not be passive ice sublimation at all. They could be thruster plumes, exhaust streams from a propulsion system designed for interstellar travel and in-system maneuvering. The geometry of the jets raised additional questions. Were they coming from discrete points on the surface, like rocket nozzles? Or were they more diffuse, like areas of enhanced outgassing? The resolution of the November 8th images wasn't quite sufficient to definitively answer this question, but some researchers analysing the data suggested they could see hints of structure, possible locations where jets originated from specific features on the nucleus. If those features were technological rather than geological, we'd be looking at thruster ports, engine exhausts, the physical evidence of a propulsion system built by an intelligence that developed under a different star, circling a different sun, possibly billions of years ago in a galaxy that might not even resemble ours. The counter-argument remained that we don't fully understand cometary behaviour, especially for interstellar comets that might have different compositions or structures than solar system comets. 3I-ATLAS spent billions of years in interstellar space, far from any star, at temperatures approaching absolute zero. The ice in its interior could have unusual crystalline structures. Trapped volatiles could be mixed with the ice in the ways we've never seen. When heated by our sun, such exotic ices might sublimate in unexpected patterns, creating jet configurations that only look artificial because we lack experience with this type of object. It's a reasonable argument, the kind of careful, scientific reasoning that keeps us from jumping to premature conclusions. But it also feels increasingly like special pleading, invoking unknown physical mechanisms to explain away observations that have a much simpler explanation if we're willing to consider it. Occam's razor suggests we should prefer the explanation that requires fewer untested assumptions. Is it simpler to postulate exotic ice physics we've never observed, or to consider that 3I-ATLAS might be using conventional physics applied through unconventional engineering? The 7-jet structure wasn't the only data point. It was one piece in an accumulating body of evidence. The missing tail, the non-gravitational acceleration, the blue coloration, the alignment of the orbit with the ecliptic, the timing of close approaches to multiple planets. Each anomaly individually could be rationalized, but taken together they formed a pattern, and patterns demand explanation. What made the November 8th discovery particularly significant was its timing. This was fresh data, images taken just 10 days after perihelion. If 3I-ATLAS was going to show its true nature, this was the moment. Maximum solar heating, maximum expected activity, and what we saw was controlled structure, not chaotic outburst. Organization, not disintegration. The astronomical community response was divided. Some researchers acknowledged the unusual nature of the observations but maintained that more data was needed before drawing conclusions. Others began openly discussing the technological hypothesis, publishing papers and giving interviews where they laid out the case for artificial origin. Still, others dismissed the entire conversation as sensationalism, insisting that 3I-ATLAS was obviously a comet and that all the anomalies would eventually be explained conventionally. But here's what none of them could ignore. The December 19th close approach was coming. 3I-ATLAS would pass within 269 million kilometers of Earth, its closest point. The James Webb Space Telescope, with its unprecedented infrared sensitivity and spectral resolution, would have its best opportunity to observe the object. Webb could detect and identify molecules in the jets. It could measure temperatures across the nucleus. It could determine the velocities of ejected material by analysing Doppler shifts in emission lines. If the jets were natural outgassing, Webb would see the signatures of water vapour, carbon dioxide, carbon monoxide, perhaps methane or ammonia. all sublimating at velocities consistent with thermal escape from a low-gravity surface. Probably 2 to 3 kilometers per second, maybe as high as 4 in some circumstances. If the jets were technological exhaust, the velocities might be much higher, 10 or 20 or 50 kilometers per second, and the composition might include ionized species that don't naturally form in cometary sublimation. One observation session with Webb could potentially settle the question. One spectrum showing exhaust velocities inconsistent with natural processes would be game-changing, but getting that observation required navigating the bureaucracy of telescope time allocation, convincing review committees that directors' discretionary time should be used for this target, and hoping that the object remained visible and active when the telescope finally pointed in its direction. The 7 jets captured on November the 8th were a snapshot, a single moment in 3I-ATLAS's journey through our solar system, but they represented something profound. They were either evidence of exotic cometary physics we'd never encountered, requiring us to revise models built on centuries of comet observations, or they were evidence of something else, entirely. Something that travelled between the stars, something that could still manoeuvre after billions of years in the cold depths of space, something that chose to be here, in our solar system, at this specific moment in time. As astronomers downloaded the November 8th images and began their analysis, as debates erupted in online forums and academic journals, one fact remained undeniable. 3I-ATLAS was not behaving like any comet we had ever seen. And with each new observation, with each new anomaly discovered, the weight of evidence was shifting. Not conclusively, not yet, but unmistakably. The object from another star system was showing us something we weren't prepared to see. The question was whether we'd have the courage to acknowledge what the evidence was telling us. Borisov's twin arrives between us and the visitor. On the morning of November the 2nd, 2025, Russian astronomer Gennady Borisov was conducting his usual survey of the night sky from his observatory at Margo in Naushny, Crimea. Borisov wasn't a newcomer to finding unusual objects. In 2019, he had discovered 2I Borisov, the second confirmed interstellar object to pass through our solar system. A comet that generated intense scientific interest and dozens of research papers. Now, 6 years later, his name was about to be attached to another discovery that would raise equally profound questions. Using his half-meter reflector telescope with its fast f1.9 focal ratio optimized for detecting faint-moving objects, Borisov identified something new in the constellation Virgo. Initial observations suggested cometary activity, a faint coma surrounding a stellar-like nucleus. By November 5th, the Minor Planet Center, the official international organization responsible for designating new solar system bodies, had received 10 reports of the object from observatories around the world. All confirmed cometary characteristics. The object received its official designation, C2025V1 Borisov. The orbital calculations came together quickly. C2025V1 was following a highly eccentric path with an eccentricity of 1.0096, with an uncertainty of 0.0026. That eccentricity value is crucial. An orbit with eccentricity exactly equal to 1 is parabolic, right on the boundary between bound and unbound from the Sun's gravity. An eccentricity greater than 1 indicates a hyperbolic orbit, an object with enough velocity to escape the solar system entirely, a truly interstellar trajectory. C2025V1's measured eccentricity was slightly above 1, technically making it hyperbolic. But here's where interpretation becomes critical. That uncertainty of 0.0026 means the true eccentricity could be anywhere from 1.0070 to 1.0122. If the actual value sits at the lower end of that range, closer to 1, 0.007, the orbit might actually be slightly elliptical when you account for gravitational perturbations from the planets. Specifically, a small gravitational impulse from Jupiter as the object passed near perihelion could be sufficient to make a bound Oort cloud object appear slightly hyperbolic in preliminary orbital fits. Avi Loeb ran the calculation backward. He integrated C2025V1's motion all the way out to 1,000 astronomical units. Far enough that planetary gravity becomes negligible. When you recompute the orbit from that distance, the eccentricity likely drops below 1. This strongly suggests the object originated from the Oort cloud. that vast spherical shell of icy debris surrounding our solar system at distances of thousands to hundreds of thousands of astronomical units. Not interstellar, despite the nearly parabolic orbit. A visitor from the outer reaches of our own solar system rather than another star. Still, that eccentricity value of essentially 1 makes C2025V1 what Loeb termed nearly interstellar. It's moving so fast that it barely remains gravitationally bound to the Sun. After its current perihelion passage on November 16th, it will swing back out to enormous distances, taking thousands or millions of years to return, if it returns at all. Slight perturbations could easily push it over the edge into a truly unbound orbit, sending it into interstellar space permanently. So we have a nearly interstellar Oort cloud object discovered just days after 3I-ATLAS, the truly interstellar visitor, passed its perihelion. Interesting timing, but perhaps coincidental. Borisov discovers comets regularly. New comets are found every year. The statistical probability of finding one in early November isn't particularly remarkable, except for one detail that should make you pause. C2025V1 was also missing its tail. The Comet Observers Database, which aggregates observations from amateur and professional astronomers worldwide, listed C2025V1 with a magnitude of 13.8 and a coma diameter of 2.3 arc-minutes. But reports of a tail were sparse and uncertain. Only 2 out of 10 initial reports mentioned seeing any tail structure at all, and those reports didn't describe the kind of prominent dust tail you'd expect from a comet approaching perihelion. On November 11th, C2025V1 would make its closest approach to Earth, passing within 0.69 astronomical units, about 103 million kilometers. That's relatively close in astronomical terms, close enough that moderate-sized telescopes should easily detect any significant tail structure. On November 16th, just 5 days later, it would reach perihelion at a distance of 0.46 astronomical units, less than half the Earth-Sun distance. At that proximity to the Sun, any normal comet should be experiencing vigorous outgassing and developing a spectacular tail. But the early observations suggested C2025V1 was remaining relatively quiet. Its brightness was increasing as it approached perihelion, yes, but not dramatically. The coma was present but not expanding rapidly. The lack of an obvious tail echoed the behaviour of 3I-ATLAS. 2 objects discovered within months of each other, both displaying cometary characteristics, but missing the most iconic feature that defines a comet in the popular imagination. The orbital geometry added another layer of intrigue. C2025V1's orbit is inclined by 112.7 degrees relative to the ecliptic plane. That's a retrograde orbit, moving in the opposite direction relative to the planets. The orbital plane is nearly perpendicular to 3I-ATLAS's orbit. If you could visualize both paths in 3-dimensional space, they'd intersect at close to a right angle. 2 objects passing through the inner solar system on wildly different trajectories, one from interstellar space and one from the Oort cloud, arriving at nearly the same time. Loeb calculated the closest separation between the 2 orbits. 75 million kilometers, or 0.5 astronomical units. But that's the minimum distance between the orbital paths themselves. The actual distance between the 2 objects depends on where they are in their respective orbits at any given time. Given their current positions and velocities, C2025V1 and 3I-ATLAS were never closer than 225 million kilometers, about 1.5 astronomical units, without accounting for any non-gravitational forces. Could they be related? Could C2025V1 somehow be associated with 3I-ATLAS? Perhaps a piece that broke off, a fragment that separated and followed a slightly different path. The orbital mechanics make this extremely difficult. The objects are on very different trajectories, with different inclinations, different eccentricities, different angular momentum vectors. For one to have originated from the other would require a substantial velocity change, a delta V of many kilometers per second. Natural fragmentation events don't produce relative velocities that large, unless, of course, one or both objects employed propulsion. If 3I-ATLAS used its thruster system to alter course, it could potentially have deployed a smaller probe or object onto a different trajectory. The 225 million kilometer separation would be trivial for an interstellar vessel capable of travelling light years between star systems. releasing a secondary object to follow a perpendicular path through the inner solar system, passing close to Earth while the primary craft swung by Mars and Venus, would be entirely feasible from an engineering standpoint. But that scenario requires accepting that 3I-ATLAS is technological, which remains controversial, and it requires C2025V1 to also be something other than a natural Oort cloud comet, despite the orbital evidence suggesting it originated from within our solar system. The hypothesis multiplies assumptions and exotic possibilities, which makes it less appealing from an Occam's razor perspective. Simpler to conclude they're unrelated objects that happen to arrive during the same general time period, yet the timing nags at anyone who looks closely. 3I-ATLAS discovered July 1st, reaching perihelion October 29th. C2025V1 discovered November 2nd, reaching perihelion November 16th. Both objects visible in Earth's sky during overlapping time windows, both displaying the unusual characteristic of muted tail development, both moving through the inner solar system on highly inclined orbits that bring them relatively close to Earth. From a human perspective, it's tempting to see patterns even in random data. Our brains evolved to detect patterns, to find connections and meaning, even when none exist. Coincidences happen. Unlikely events occur regularly simply because of the vast number of possible events that could occur. Two unusual comets arriving in the same season isn't impossible, isn't even particularly improbable, given the number of comets in the Oort cloud and the occasional interstellar visitors we're starting to detect. But there's a difference between seeing patterns in random noise and recognizing patterns in structured data. The question is which category this falls into. Are we looking at random coincidence, two unrelated objects whose overlapping appearance generates false signals of connection? Or are we looking at structured data, multiple related phenomena that we're struggling to understand because the underlying structure remains hidden? C2025 of V1's position in space on November the 7th placed it almost directly between Earth and 3I-ATLAS. Not perfectly aligned, but roughly in the same general direction from Earth's perspective. An observer on Earth looking toward Virgo in early November would be looking at C2025V1 in the foreground, with 3I-ATLAS farther beyond. Like looking at two aircraft at different altitudes but similar bearing from your position on the ground. Was this positioning meaningful? Did C2025V1 serve some purpose relative to 3I-ATLAS? Or was it simply the chance result of orbital mechanics and our viewing perspective from Earth? The scientific method demands we not jump to conclusions, that we gather more data, test hypotheses rigorously, eliminate alternative explanations systematically before embracing exotic interpretations. But the scientific method also demands we follow the evidence wherever it leads, even when it leads toward conclusions that challenge our assumptions about what's possible or likely. If the evidence suggests two objects are related, we have an obligation to seriously consider that possibility, to design observations that could test it, to calculate what predictions the relationship would make that could then be verified or falsified. Over the following days, as C2025V1 approached Earth and then continued toward perihelion, telescopes worldwide would track its behaviour. Would it develop the expected bright tail as solar heating intensified? Would it brighten dramatically as fresh ice sublimated from its nucleus? Would it behave like a normal Oort cloud comet, validating the conventional interpretation? Or would it continue to defy expectations, remaining stubbornly quiet, maintaining its compact appearance, acting less like a passive chunk of ice and more like something else? The discovery of C2025V1 transformed the conversation around 3I-ATLAS from speculation about a single anomalous object to questions about multiple objects and their potential relationships. It provided a comparison case, a nearly interstellar comet, from our own solar system that we could observe alongside the truly interstellar visitor. By studying how they differed, how they resembled each other, we might learn something profound about both. Or we might learn something terrifying, something about coordination and timing, something about missions and objectives, something about visitors from the stars who don't just pass through randomly, but arrive with purpose, with planning, with capabilities we're only beginning to glimpse. The twin had arrived. Now we needed to determine whether it was coincidence or design. Two comets without tails in the same week. Let's talk about probability. Not the kind of vague intuition we all have about what seems likely or unlikely, but actual statistical analysis, hard numbers, the mathematics of coincidence versus causation. Because when you examine what happened during the first 2 weeks of November 2025, the numbers become impossible to ignore. Start with the baseline. How common are comets? In any given year, several dozen comets are discovered, though most are faint objects detected only by professional surveys or dedicated amateur astronomers with serious equipment. Of those, perhaps 10 to 20 become bright enough to observe with small telescopes. Maybe 1 or 2 per year become naked-eye objects visible to casual observers. The vast majority remain faint, unremarkable, behaving exactly as models predict. Now consider tail development. The iconic cometary tail, streaming millions of kilometers behind the nucleus, is the defining visual characteristic of these objects. Not every comet develops a prominent tail at every stage of its orbit, but near perihelion, when solar heating reaches maximum intensity, tail formation is essentially universal among active comets. Of the thousands of cometary perihelion passages observed throughout history, vanishingly few have failed to produce detectable tails when observed, with appropriate instruments under favourable conditions. There are exceptions, of course. Some comets fragment and disintegrate completely. Others turn out to be extinct, their volatile ice is depleted after too many previous passes near the Sun, leaving behind inert rocky cores that no longer outgas. But these are unusual cases, notable precisely because they deviate from the norm. An active comet with a substantial coma indicating ongoing outgassing that fails to produce a visible tail near perihelion is rare. Not impossible, but rare enough that each case generates scientific papers examining what unusual circumstances might explain the anomaly. 3I-ATLAS displayed exactly this rare behaviour. Despite clear evidence of activity, despite the coma detected by every telescope pointed its direction, despite the non-gravitational acceleration indicating substantial mass ejection, the November images showed no prominent tail. The object remained compact, the surrounding halo relatively small and symmetric rather than extended and swept back by solar radiation pressure. Then, within days, C2025V1 appeared. Another comet, another object showing activity in a coma, another object approaching perihelion, and another object conspicuously lacking the expected tail. 2 rare anomalies, occurring simultaneously in the same region of sky, visible from Earth during overlapping time periods. What are the odds? Let's construct a rough calculation. Suppose the probability of an active comet failing to develop a visible tail near perihelion under good observing conditions is 1 in 100. That's probably generous, probably an overestimate, but we'll use it to be conservative. The probability of this happening to 2 independent comets is 1 in 100 times 1 in 100, which equals 1 in 10,000, or 0.01%. But that calculation assumes the 2 events are independent, that C2025V1's tail, or lack thereof, has no relationship to 3I-ATLAS. If they're somehow connected, if there's a common cause or relationship, the probability calculation changes entirely. The compound probability no longer applies. Instead, we'd be looking at a single phenomenon manifesting in 2 objects, which has whatever probability that phenomenon itself possesses. The perpendicular orbital planes add another statistical wrinkle. Comets from the Oort cloud can arrive from any direction with roughly equal probability. The spherical Oort cloud surrounds the solar system in all directions, and objects falling inward from it can have orbits inclined at any angle relative to the ecliptic. But most comets we observe have orbital inclinations distributed randomly across all possible angles. Finding 2 comets with nearly perpendicular orbital planes, both visible from Earth at the same time, isn't particularly rare by itself. But combined with everything else, it becomes part of a larger pattern. Consider the discovery dates. 3I-ATLAS was identified July 1st, but pre-discovery images showed it as far back as May 8th in transiting exoplanet survey satellite data. C2025V1 was discovered November 2nd. The time between discoveries is just over 4 months. In a typical year, multiple comet discoveries occur within 4-month windows. Nothing unusual there. But these aren't typical comets. One is interstellar, only the 3rd such object ever detected. The other is nearly interstellar with an eccentricity barely allowing it to remain gravitationally bound to the Sun. The probability of discovering any interstellar object in a given year is difficult to estimate because our sample size is tiny. 3 confirmed interstellar objects over roughly 8 years since Oumuamua in 2017. That's less than 1 per 2 years on average. Of course, detection probability depends heavily on survey capability, which has been improving, so the true arrival rate could be higher than observed discovery rate. But even being generous, interstellar objects are rare events. Nearly interstellar objects from the Oort cloud are less rare but still uncommon. Most Oort cloud comets have eccentricities well below 1, following elliptical orbits that bring them back to the inner solar system on predictable schedules, though often with orbital periods of thousands or millions of years. Objects with eccentricities extremely close to 1, like C2025V1, represent the tail end of the distribution, comets given just barely enough energy to escape but not quite achieving it. Maybe a few percent of Oort cloud comets fall into this nearly interstellar category, so we have an interstellar object and a nearly interstellar object, both active, both lacking prominent tails, both visible from Earth within overlapping time periods, moving on perpendicular orbital planes. Each individual characteristic has some probability. The compound probability of all characteristics occurring together in 2 independent objects becomes vanishingly small. Not zero, impossible to definitively call impossible, but so unlikely that it demands explanation beyond mere chance. This is where Bayesian reasoning becomes useful. Start with prior probabilities, our initial estimates of how likely different scenarios are before considering the new evidence, then update those probabilities based on the evidence we observe. If a scenario that initially seemed unlikely predicts the evidence we're seeing while more likely scenarios don't, we should update our probability estimates accordingly. The default scenario, the one with the highest prior probability, is that 3I-ATLAS and C2025V1 are unrelated natural objects. 3I-ATLAS is an interstellar comet that happens to show unusual behaviour. C2025V1 is an Oort cloud comet that also happens to show unusual behaviour. Their simultaneous appearance is coincidence. This scenario doesn't require any exotic physics or unprecedented phenomena. It just requires that 2 unlikely but possible events occurred during the same time window. But this scenario doesn't predict the evidence well. It doesn't explain why both objects lack tails. It doesn't account for the timing of their discoveries and perihelion passages. It treats each anomaly as independent when the clustering of anomalies suggests possible connection. Under Bayesian updating, scenarios that better predict the observed evidence should receive higher posterior probability, even if they had lower prior probability. Alternative Scenario 1. Both objects are natural, but their unusual behaviour stems from a common external cause. Perhaps some aspect of the solar environment during this particular time period affects how comets sublimate or develop tails. Maybe the solar wind conditions, the interplanetary magnetic field configuration, or some other space weather parameter creates circumstances where tail formation is suppressed for any comet passing through. This would explain the shared anomaly, while maintaining that both objects are natural. But solar wind and space weather don't vary that dramatically on the timescales we're discussing. Conditions in early November weren't radically different from conditions in October or September. Other comets observed during this period, like Comet Lemon, showed perfectly normal tail development. If space weather was suppressing tails, it should affect all comets, not just these 2 specific objects. Alternative Scenario 2. One or both objects are not entirely natural. If 3I-ATLAS is a technological artifact using propulsion systems, its lack of a tail makes perfect sense. High-efficiency thrusters could produce the observed acceleration while ejecting minimal mass at high velocity, not enough to create a visible tail. If C2025V1 is related to 3I-ATLAS, perhaps a deployed probe or sub-satellite, it might employ similar technology for course corrections, again explaining the lack of a prominent tail. This scenario predicts the evidence extremely well. It explains both tailless objects. It provides a mechanism for their potential relationship despite perpendicular orbits. It accounts for the precision timing, but it requires accepting that at least one object is technological, which has enormous implications and naturally faces significant skepticism. The prior probability most scientists would assign to alien artifacts in our solar system is very low, though perhaps not as low as it should be given the vastness of the galaxy and the age of the universe. The mathematical framework of Bayesian reasoning tells us we should increase our credence in scenarios that successfully predict surprising evidence, even if those scenarios initially seemed unlikely. How much we increase our credence depends on how surprising the evidence is and how well the scenario explains it, compared to alternatives. The two tailless comets in the same week is surprising evidence. Very surprising. The technological scenario explains it much better than the independent coincidence scenario. Does this prove 3I-ATLAS and C2025V1 are technological? No. Proof requires much higher standards, but it shifts the probabilities. It makes the possibility more plausible than it was before we observed these two objects together. And as additional evidence accumulates, the probabilities continue to shift bit by bit, observation by observation, until at some point we might reach a threshold where the technological explanation becomes not just possible, but likely, then probable, then eventually the only reasonable conclusion that fits all the data. We're not there yet. The evidence is suggestive, but not conclusive. Mainstream astronomy remains committed to natural explanations, searching for exotic cometary physics or unusual circumstances that could account for the anomalies without invoking artificial objects. That's appropriate scientific conservatism, refusing to abandon conventional explanations prematurely. But conservatism can become stubbornness if it refuses to update probabilities in the face of mounting evidence. The perpendicular orbits create another angle worth examining. If you wanted to survey the inner solar system efficiently, sending multiple probes to observe different planets in different regions of space, how would you arrange their trajectories? You'd want orbits at different inclinations to provide comprehensive coverage. Perpendicular orbits would be particularly useful because they sample completely different geometries, different viewing angles, different regions of the heliosphere and magnetosphere. Earth's orbit lies in the ecliptic plane. Most planets orbit close to this plane. 3I-ATLAS came in at a slight angle, within 5 degrees of the ecliptic, allowing it to pass relatively close to Mars, Venus, and eventually Jupiter. Perfect geometry for observing the inner planets. C2025V1 came in perpendicular to the ecliptic, providing a completely different vantage point, approaching Earth from above or below the plane depending on the perspective. From a mission design standpoint, this makes sense. From a random arrival standpoint, it's just one more curious detail in a growing list of curious details. Each detail individually might not mean much, but collectively they paint a picture. Whether that picture represents reality or pareidolia, seeing patterns in randomness remains the central question. Over the coming weeks, both objects would continue their journeys through the inner solar system. C2025V1 would reach perihelion on November 16th. 3I-ATLAS would approach its December 19th closest pass by Earth. Telescopes worldwide would gather data, measure spectra, track brightness changes, search for any signs of tail development, or other characteristic behaviors. The evidence would continue to accumulate, the probabilities would continue to shift, and eventually, one way or another, we would have our answer. Two comets without tails weren't impossible, but they demanded explanation, and the explanation we ultimately accepted would reshape how we understood our place in the cosmos. Solar storms, earthquakes, and interstellar timing picture November 7th, 2025, as a moment when multiple cosmic forces converged. At 5:17 Universal Time, a coronal mass ejection slammed into Earth's magnetosphere with solar wind velocities exceeding 800 kilometers per second. The geomagnetic field responded violently, surging to G3 strong storm conditions within hours. Auroras danced across 22 states. Power grids strained under induced currents. GPS systems reported increasing errors. At that exact same moment, 3I-ATLAS was 1.4 astronomical units from the Sun, just days past its October 29th perihelion, in the region where solar heating should be triggering maximum outgassing from any natural comet. Instead, it showed the puzzling lack of a substantial tail, those 7 mysterious jets oriented in multiple directions, that compact structure suggesting something other than passive ice sublimation. Simultaneously, C2025V1 was closing in on Earth, just 4 days from its November 11th closest approach, moving through space on its perpendicular trajectory, also missing the expected cometary tail, also defying standard predictions about how these objects should behave. 3 phenomena, one moment in time, solar maximum activity bombarding Earth with electromagnetic fury. An interstellar object showing technological signatures, a nearly interstellar object appearing precisely when and where it could serve as comparison or companion. Is this convergence meaningful, or are we seeing patterns where none exist, connecting dots that randomness scattered across the canvas of space and time? Let's examine the timing more carefully. The solar storms of early November weren't unique or unprecedented in isolation. Solar maximum occurs every 11 years as part of the Sun's natural activity cycle. We're currently in solar cycle 25, which began in December 2019 and is expected to peak sometime between 2024 and 2026. Peak solar maximum is when sunspot numbers reach their highest, when active regions most frequently produce powerful flares, when coronal mass ejections bombard Earth most intensely. November 2025 falls right in this peak window. We should expect intense solar activity. The X-class flares and G3 geomagnetic storms are par for the course during solar maximum. Nothing unusual about their occurrence. What's unusual is their timing relative to 3I-ATLAS perihelion and C2025V1's discovery and approach. 3I-ATLAS reached perihelion on October 29th. Peak solar activity occurred in the days immediately following, November 4th through 9th. If 3I-ATLAS was observing solar activity, if it was interested in how our star behaves, if it was gathering data on the star that it's now visiting after billions of years travelling through interstellar space, the timing would be ideal. Arrive at closest approach just before a major outburst. Position yourself to measure the solar wind, the coronal mass ejections, the radiation environment, all at maximum intensity. But here's where the earthquake connection becomes deeply unsettling. Remember that 27 to 28 day window. The correlation between geomagnetic storms and earthquake occurrence, with the earthquake probability increasing roughly 4 weeks after intense space weather. Count forward from November 7th, add 27 days, you arrive at December 4th. Add 28 days, and you reach December 5th. A window of elevated seismic risk predicted by the statistical correlation, falling in the days immediately after 3I-ATLAS comes closest to Earth on December 19th. Wait, those dates don't line up exactly. The earthquake window would be early December, while the closest approach is mid-December. But consider the sustained nature of the solar bombardment. Multiple CMEs hit Earth between November 5th and November 10th. Each one could set its own 27 to 28 day timer. The compound effect of several geomagnetic storms in quick succession might create an extended window of elevated earthquake probability stretching from late November through mid-December. Now layer in another factor. The research on solar proton density showed a 1-day delay between solar wind peaks and earthquake probability increases. The intense solar activity of November 4th through 9th would predict elevated seismic risk for November 5th through 10th. And indeed, the Afghanistan magnitude 6.3 earthquake occurred on November 3rd, right at the beginning of this period, possibly responding to elevated solar wind from earlier storms that preceded the main November barrage. We're looking at multiple overlapping mechanisms and timeframes. Immediate effects from proton density spikes. Delayed effects from geomagnetic storm-induced telluric currents. All playing out while two unusual objects traverse the inner solar system during the same time period. If you wanted to observe how a planetary system responds to space weather stress, to measure the coupling between stellar activity and geological phenomena, to gather data on earthquake triggering mechanisms, this would be the perfect experimental setup. Could 3I-ATLAS have planned its arrival to coincide with solar maximum? Could it have calculated an orbital trajectory that would bring it to perihelion during the most active phase of our Sun's 11-year cycle? The object has been travelling for billions of years, covering light-years of interstellar space. The precision required to time arrival at a specific star during a specific phase of that star's activity cycle would be extraordinary, but perhaps not impossible for a sufficiently advanced navigation system. Think about how we plan missions to other planets. We use Hohmann transfer orbits, gravity assist maneuvers, launch windows that optimize fuel efficiency and travel time. We calculate exactly when to launch from Earth so that our spacecraft arrives at Mars or Jupiter when those planets are optimally positioned. The same principles apply to interstellar travel, just on vastly larger scales with much longer planning horizons. An object departing from a star system 5 or 10 or 20 light-years away, aiming for our solar system, would need to account for the motion of both stars through the galaxy. It would need to predict where our sun would be at the time of arrival, millions or billions of years in the future. Getting close would be challenging but feasible with accurate stellar motion data, but timing arrival to coincide with solar maximum, with a specific phase of an 11-year cycle, would require knowledge of our sun's behaviour patterns, observations made from the origin system before departure, models predicting cyclic activity. Is that level of sophistication plausible? For a civilization capable of building interstellar vehicles that remain functional after billions of years in the void, that can still manoeuvre and navigate after crossing light years of space, it doesn't seem beyond possibility. It might even be expected. Why send an exploratory mission without optimizing its arrival time to maximize scientific return? The C2025V1 connection adds another dimension. If it's a deployed probe rather than an independent Oort cloud comet, its appearance during the same window of peak solar activity and earthquake prediction makes sense. You wouldn't just send a single vehicle to observe a planetary system. You'd send multiple instruments, multiple platforms, each positioned to gather different types of data from different vantage points. The perpendicular orbits would provide comprehensive coverage, multiple views of the same phenomena from different geometries. But let's play devil's advocate. Let's steelman the coincidence argument. Solar maximum occurs every 11 years and lasts roughly 2 to 3 years. That means at any given moment, there's about a 20 to 30% chance we're in or near solar maximum. Not particularly improbable. Interstellar objects might pass through our solar system every few years or decades. We don't know the rate precisely because our detection capabilities only recently became adequate to spot them. Finding one during solar maximum isn't remarkably unlikely. C2025V1 is an Oort cloud comet, and new Oort cloud comets are discovered regularly, dozens per year. Some will, inevitably, be nearly interstellar with eccentricities close to 1. Some will be discovered during solar maximum simply because that's when we happen to be observing. The perpendicular orbits result from the random distribution of Oort cloud comet trajectories. The missing tails could both result from unusual but natural circumstances we don't fully understand yet. Under this interpretation, every piece of evidence has a conventional explanation. The overall pattern emerges from our tendency to find meaning in randomness, to construct narratives that connect unrelated events. Humans evolved to detect patterns because pattern detection provided survival advantages. Better to see a predator lurking in ambiguous shadows than to miss the threat. But this same cognitive architecture makes us prone to false positives, seeing design where only chance exists. The question becomes, at what point does accumulated coincidence become so unlikely that we're justified in considering alternative explanations? How many low probability events need to cluster together before we acknowledge the cluster itself requires explanation beyond chance? This is the fundamental challenge of anomaly assessment, of deciding when data crosses the threshold from curious to significant. Standard scientific practice sets that threshold quite high, demanding extraordinary evidence for extraordinary claims. The extraordinary claim here is that 3I-ATLAS might be technological, that C2025V1 might be related to it, that their arrival during peak solar activity might be intentional rather than accidental. Those claims challenge fundamental assumptions about our place in the universe, about whether we're alone, about whether other intelligences exist and occasionally visit our stellar neighbourhood. But extraordinary evidence is accumulating. The missing tails despite clear activity and non-gravitational acceleration. The 7-jet structure inconsistent with passive outgassing, the orbital alignments and timing, the perpendicular trajectories providing complementary coverage, the convergence with solar maximum and predicted earthquake windows. Each piece of evidence might not be extraordinary by itself, but the collection, the pattern, the clustering, that's what matters. December looms ahead with multiple critical dates. December 4th and 5th, the predicted earthquake window from the early November geomagnetic storms. December 19th, 3I-ATLAS closest approach to Earth. The James Webb Space Telescope observations that might finally measure jet velocities and compositions definitively. Each date represents a test, an opportunity for the universe to show us whether patterns we're seeing are real or illusory. If significant earthquakes strike during the predicted window, it validates the solar-terrestrial coupling mechanism, confirming that space weather influences seismic activity on predictable timescales. If Webb observations show exhaust, velocities consistent with technological propulsion rather than natural sublimation, it transforms 3I-ATLAS from mysterious comet to confirmed artifact. If C2-025V1 continues to behave anomalously through perihelion, lacking the dramatic brightening and tail development expected from Oort cloud comets, it strengthens the case for some connection to 3I-ATLAS. Or perhaps none of these predictions will be borne out. Perhaps earthquakes will occur randomly, unrelated to geomagnetic storm timing. Perhaps Webb will see normal cometary emissions with velocities and compositions indistinguishable from natural outgassing. Perhaps C2025V1 will suddenly develop a spectacular tail as it heats up, revealing itself as an ordinary comet that just happened to be quiet during early observations. That outcome would suggest we've been seeing phantoms, constructing elaborate theories from incomplete data and pattern-matching instincts. It would be humbling but also reassuring in its way. The universe remaining comprehensible within established frameworks, not requiring radical revision of our understanding. Just comets being comets, solar storms being solar storms, earthquakes being earthquakes, all following natural laws without hidden connections or intelligent orchestration. But if the predictions hold, if the patterns persist, if the evidence continues pointing toward coordination and design, then we face a fundamentally different reality. One where objects from other stars can arrive with precision timing, where geological processes on Earth respond to electromagnetic forces from the Sun, where the solar system we thought we knew reveals itself to be more active, more connected, more observed than we ever imagined. The convergence of solar storms, earthquakes, and interstellar timing wouldn't be coincidence. It would be data telling us something profound about the universe and our place within it. What Webb will reveal on December 19th to December 19th, 2025. Mark that date. Write it down. Set a reminder. Because on that day, 3I-ATLAS will pass within 269 million kilometers of Earth, roughly 1.8 astronomical units, its closest approach to our planet during its entire passage through the solar system. For astronomers, for space agencies, for anyone who's been following this story, December 19th represents the moment of truth, the day when our most powerful observational tools will have their best opportunity to determine what 3I-ATLAS actually is. The James Webb Space Telescope orbits the Sun at the L2 Lagrange point, about 1.5 million kilometers from Earth, in the direction away from the Sun. From that vantage point, Webb's instruments can observe the cosmos without interference from Earth's atmosphere or the thermal glow from our planet. Its infrared sensors, operating at temperatures just above absolute zero, can detect the faintest heat signatures from objects billions of light years away. But on December 19th, those instruments will be pointed much closer to home. Webb's near-infrared spectrograph, NIRSpec, can split light into its component wavelengths with extraordinary precision. When molecules vibrate or rotate, they absorb and emit infrared light at specific frequencies determined by their atomic structure and quantum mechanical energy levels. Each molecule has a unique spectral fingerprint. Water vapor looks different from carbon dioxide, which looks different from carbon monoxide, which looks different from methane or ammonia, or any of the dozens of other molecules that might be present in a cometary coma or jet. But NIRSpec can do more than just identify molecules. It can measure their velocities using the Doppler effect. When molecules move toward us, their spectral lines shift toward shorter wavelengths, blue shifted. When they move away, the lines shift toward longer wavelengths, red shifted. The amount of shift tells us the velocity precisely. For cometary outgassing, thermal sublimation from an icy surface produces gas velocities typically between 2 and 4 kilometers per second, determined by the temperature and the molecular weight of the gas. Chemical rocket exhaust, 3 to 5 kilometers per second. Ion thruster exhaust, 10 to 50 kilometers per second or even higher. These ranges don't overlap. The velocity distribution alone could distinguish between natural sublimation and technological propulsion. One observation, one spectrum showing jets moving at 10 or 20 kilometers per second would be game-changing. It wouldn't just suggest 3I-ATLAS is artificial, it would prove it beyond reasonable doubt. Webb can also measure temperatures. The mid-infrared instrument, MIRI, operates at wavelengths where thermal emission from solid surfaces peaks for objects at hundreds of degrees above absolute zero. A natural comet's nucleus, heated passively by sunlight, reaches specific temperatures determined by its albedo, how much light it reflects versus absorbs, and its thermal inertia, how quickly it heats and cools. These temperatures are predictable, calculable, constrained by physics. But an active technological object might show different thermal signatures, localized hotspots where thruster ports generate high temperatures, thermal patterns inconsistent with passive solar heating, temperature distributions that require internal heat sources. MIRI could detect these signatures if they exist. The challenge is getting telescope time. Webb's schedule is planned years in advance through a competitive proposal process. Research teams from around the world submit observing proposals. Expert panels review them, rank them by scientific merit, and allocate the available time to the highest priority projects. Directors' discretionary time exists for targets of opportunity, unexpected phenomena that couldn't be planned for, but it's limited and carefully guarded. 3I-ATLAS was discovered in July, after the proposal cycle for late 2025 observations had already closed. Follow-up observations during August and September used the time allocated months earlier for other approved programs, squeezing in a few orbits here and there when schedule gaps allowed. But comprehensive characterization during the December close approach. That would require dedicated observing time, multiple visits with multiple instruments, coordinated campaigns lasting days or weeks. As of early November, no such campaign had been officially announced. NASA's public statements emphasized that multiple telescopes, including Webb, had observed 3I-ATLAS earlier in its approach. The agency highlighted the scientific value of studying an interstellar comet, the opportunity to analyze material from another star system, the potential insights into planetary formation elsewhere in the galaxy, all framed within the conventional interpretation that 3I-ATLAS is a natural object, unusual perhaps, but fundamentally explicable within established astrophysics. But behind the scenes, conversations were happening. Researchers with access to decision-makers were making the case for December observations. The anomalies, the unanswered questions, the potential implications if 3I-ATLAS turned out to be something other than a comet. Some arguments focused on pure science, the unique opportunity to characterize an interstellar visitor at close range. Other arguments touched on more speculative possibilities, the need to know whether we're being observed, whether an intelligence from another star has sent something to study our solar system. Those speculative arguments face institutional resistance. Space agencies are conservative organizations, cautious about association with fringe theories or sensational claims. The scientific community values careful methodology over premature conclusions. Nobody wants to be the person who cried alien only to have the object turn out to be a weird comet. Professional reputations, grant funding, career trajectories all hang on being right, or at least being defensively careful, yet the stakes justify the risk. If there's even a 10% chance, even a 1% chance that 3I-ATLAS represents an artificial object, the implications are so profound that investigation becomes imperative, regardless of how unlikely the scenario might seem. This is the logic of low probability, high consequence events. You prepare for them not because they're likely, but because the cost of being unprepared is unacceptable. Webb observations during December could resolve multiple questions simultaneously. The jet velocity measurements would distinguish natural versus technological propulsion. The molecular composition would reveal whether the outgassing matches known cometary compositions or shows anomalies suggesting exotic materials or engineered processes. The thermal mapping would indicate whether the surface temperature distribution is consistent with passive solar heating or requires additional heat sources. But here's what makes December 19th so critical beyond just the Webb observations. It's not only when 3I-ATLAS comes closest to Earth, it's also when ground-based telescopes have their best viewing geometry. The object will be reasonably well separated from the Sun in Earth's sky, avoiding the glare that hampered earlier observations. It will be at moderate altitude for observatories in both hemispheres, accessible to instruments worldwide, and it will still be relatively close, bright enough for detailed imaging and spectroscopy with professional-class equipment. Amateur astronomers with serious equipment will also have their shot. The distributed network of observers, the dedicated individuals who spend cold nights at telescopes tracking comets and asteroids and variable stars, often spot details that large surveys miss. The collective data from dozens or hundreds of observers, pooled and analysed, can reveal patterns and changes that single observations might overlook. If 3I-ATLAS does anything unusual during its close approach, someone will notice. The predictions about what we'll see depend heavily on which hypothesis you favour. If 3I-ATLAS is natural, Webb should observe water vapour, carbon dioxide, carbon monoxide, possibly complex organic molecules, all moving at thermal velocities of 2 to 4 kilometers per second. The temperature distribution should show a gradient from hotter day side to cooler night side consistent with a rotating nucleus heated by the sun. The overall behaviour should match refined models of interstellar comet evolution, even if those models need adjustment to account for the object's unusual characteristics. If 3I-ATLAS is technological, Webb might see very different signals. Exhaust velocities above 10 km per second indicating high-efficiency propulsion, ionized species, atomic emissions or molecular radicals that don't form naturally in cometary sublimation, localized temperature peaks suggesting active systems, spectral features that can't be explained by passive heating and ice sublimation. Any one of these signatures would be extraordinary. Multiple signatures together would be definitive. There's also the possibility of intermediate results, data that doesn't clearly support either hypothesis, observations that raise as many questions as they answer, velocities in the ambiguous range between thermal escape and clear propulsion, compositions that are unusual but potentially natural, thermal patterns that are odd but not impossible to explain with exotic ice structures or rotation states. Science often works this way, incremental progress rather than sudden revelations, gradually narrowing the range of viable explanations rather than immediately identifying the correct one. But December 19th offers something beyond gradual progress. It offers the potential for decisive evidence. The geometry, the proximity, the accumulated months of prior observations establishing baseline behaviour, all combine to make this the moment when definitive characterization becomes possible. If Webb observes, if the weather cooperates, if the instruments perform as designed, if the data reduction and analysis proceed without complications, we could have answers within days or weeks of the close approach. Then there's the matter of data release. NASA has policies about public access to astronomical data. Generally, observations become public after a proprietary period, allowing the research teams who propose the observations to analyse and publish their findings first. But for targets of exceptional public interest, especially those with potential implications beyond pure science, expedited release sometimes occurs. Would Webb observations of 3I-ATLAS during its closest approach to Earth fall into that category? The public fascination with 3I-ATLAS has been building steadily since summer. Social media discussions, YouTube videos, podcast episodes, online forums debating the evidence and speculating about possibilities. Mainstream media coverage, initially dismissive or superficial, has gradually become more serious as the anomalies accumulated and reputable scientists began speaking openly about technological possibilities. By December, the attention will be intense. Millions of people worldwide will be watching, waiting for news, eager to know what the most powerful telescope ever built reveals about this visitor from the stars. In that environment, keeping data locked behind proprietary periods for months or years would be politically difficult and perhaps ethically questionable. If Webb sees something extraordinary, something that definitively identifies 3I-ATLAS as artificial, can that information be withheld while researchers draft papers and go through peer review? The protocols aren't designed for this situation. For observations with implications extending far beyond academic astronomy into questions of global significance. December 19th is also significant for another reason. It falls within that predicted earthquake window extending from late November through mid-December, the 27 to 28-day delay after the early November geomagnetic storms. If the solar-terrestrial coupling mechanism is real, if space weather does influence seismic activity on that timescale, then earthquakes during this period would validate the correlation precisely when our attention is focused on 3I-ATLAS and its closest approach to Earth. The convergence wouldn't be coincidence, it would be synchronization. Imagine the scenario. Early December, significant earthquakes strike in seismically active regions, following the predicted schedule after November's intense geomagnetic activity. Mid-December, 3I-ATLAS approaches Earth. Webb observations revealing jet velocities and compositions inconsistent with natural comets. Preliminary data suggesting technological origin. Social media erupts. News networks scramble to update their coverage. Scientists debate interpretation and implications, and humanity collectively grapples with the possibility, rapidly becoming probability, that we're not alone, that others exist, that something from another star has come to visit our solar system during a moment of intense solar activity and geological response. Or perhaps December 19th brings anticlimax. Webb observations showing perfectly normal cometary emissions, thermal escape velocities, conventional compositions. 3I-ATLAS revealed as unusual but natural, its anomalies explained by exotic ice structures or atypical formation history. The earthquakes, if they occur, falling outside predicted windows or showing no statistical correlation with geomagnetic activity. The entire edifice of speculation and hypothesis crumbling under the weight of prosaic data. That outcome would teach valuable lessons about not over-interpreting ambiguous evidence, about the importance of waiting for definitive data before drawing conclusions, about how easy it is to construct compelling narratives from incomplete information. It would be humbling but healthy, a reminder that the universe doesn't cater to our desires for drama or significance, that cosmic visitors can be strange without being artificial, that patterns sometimes emerge from randomness without deeper meaning. But the evidence we have now, the observations accumulated over months, the multiple independent anomalies, the timing and geometry, all point toward December 19th being much more than anticlimax. Whatever Webb reveals, whatever ground-based telescopes capture, whatever data emerges from humanity's best instruments trained on this object from another star, it will be important. It will matter. It will tell us something profound about the cosmos and our place within it. December 19th, 2025. The day we learn the truth about 3I-ATLAS. The day everything might change. The control experiment we didn't ask for. In any scientific investigation, the control is crucial. You need a baseline, a comparison case, an example of normal behavior against which anomalies can be measured. Without controls, you can't distinguish between unusual conditions and measurement errors. Without controls, every deviation looks potentially significant when it might simply represent natural variation. C2025V1 Borisov, whether by cosmic coincidence or deliberate design, provides exactly that control for understanding 3I-ATLAS. Here's an object we know originated from within our solar system. The orbital calculations, even accounting for uncertainties, place its source in the Oort cloud with high confidence. It's gravitationally bound to the Sun, barely, but bound, nonetheless. Its composition should match other Oort cloud comets, which formed from the same primordial material as everything else in our solar system, 4.6 billion years ago. If we understand comets at all, if our models of how these objects behave have any validity, C2025V1 should follow predictable patterns. On November 11th, it made its closest approach to Earth, passing within 103 million kilometers. Telescopes worldwide trained on it, capturing images and spectra. On November 16th, it would reach perihelion at 0.46 astronomical units, less than half Earth's distance from the Sun. At that proximity, solar heating would be intense, far more intense than 3I-ATLAS experienced at its more distant 1.36 astronomical unit perihelion. If any comet was going to develop a spectacular tail, C2025V1 should be that comet. The observations from November 11th showed a compact object with a coma measuring 2.3 arc-minutes in diameter. The apparent magnitude was 13.8, reasonably bright for a modest telescope but not naked eye visible. The coma indicated active sublimation, gas and dust being released from the nucleus, all normal so far. But where was the tail? Reports remained sparse and uncertain. Most observers noted the coma but couldn't detect a clear tail structure. Those who reported seeing something that might be a tail described it as faint, poorly defined, much less prominent than expected for an object approaching perihelion. This pattern echoed 3I-ATLAS. Active outgassing producing a coma, but tail development suppressed or delayed relative to predictions. Now here's where the control experiment aspect becomes powerful. If both 3I-ATLAS and C2025V1 fail to develop prominent tails despite clear evidence of activity, we need to ask why. Is there something about the current space environment, the solar wind conditions, the interplanetary medium, that's suppressing tail formation for any comet passing through during this time period? If so, we'd expect other comets observed during the same weeks to show similar behaviour. Comet Lemon, remember, was imaged on November 3rd showing a perfectly normal textbook quality tail streaming away from the Sun. Lemon is a solar system comet, discovered in 2021, following a slightly elliptical orbit that brings it through the inner solar system periodically. When it passed perihelion in October 2025, just weeks before 3I-ATLAS and C2025V1, it behaved exactly as cometary physics predicts. Clear tail, obvious dust emissions, no anomalies, so the space environment isn't universally suppressing tails. Lemon developed one. That means the missing tails on 3I-ATLAS and C2025V1 must result from something specific to those objects, not the general conditions they're passing through. This is the power of having a control and a comparison all at once. Lemon shows us what normal looks like. C2025V1 shows us what our own Oort cloud comets do under current conditions. And 3I-ATLAS shows us something different. But wait, C2025V1 is also missing its tail, or at least displaying a greatly suppressed one. That suggests it's not normal either. If it's an Oort cloud comet, if it's definitely natural, if it should behave like Lemon, why isn't it? This is where the interpretation gets tricky, and the value of having this particular control becomes both illuminating and confusing. One possibility is that C2025V1 truly is a natural Oort cloud comet, but one with unusual properties. Maybe its composition differs from typical comets. Oort cloud objects spent billions of years at extreme distances where temperatures approach absolute zero. Cosmic ray bombardment over those timescales could alter the structure of ices, creating unusual crystalline forms or chemical modifications. When such exotic ices finally get heated by the Sun, they might sublimate differently than normal water ice or carbon dioxide ice. Or perhaps C2025V1's nearly parabolic orbit, with eccentricity so close to 1, indicates it was kicked outward from the inner Oort cloud relatively recently by a passing star or giant molecular cloud. It might be making its first pass through the inner solar system after billions of years of quiescence. First-time comets sometimes behave differently than more evolved objects. The pristine ices, never heated before, might have properties we haven't characterized well because we've mostly studied comets that have made multiple perihelion passages. These explanations preserve C2025V1 as a natural object while accounting for its anomalous behavior. The control still works. It shows us that natural Oort cloud comets can sometimes display suppressed tail development under specific circumstances. Therefore, 3I-ATLAS missing its tail might also result from natural causes, just particularly unusual natural causes that we're encountering for the first time with these two objects. But this interpretation has problems. It requires two rare conditions occurring simultaneously. 3I-ATLAS, an interstellar comet, happens to have exotic ices that suppress tail formation. C2025V1, an Oort cloud comet, also happens to have exotic ices that suppress tail formation. Both objects, from completely different source regions formed under different stars or in different parts of our protosolar nebula, arriving in the inner solar system at the same time, both displaying the same rare anomaly. That's a lot of coincidence to swallow. The alternative interpretation flips the control experiment on its head. What if C2025V1 isn't actually a natural Oort cloud comet? What if it's related to 3I? ATLAS deployed or released or coordinated to arrive simultaneously. In that scenario, its suppressed tail development makes perfect sense. It's using similar propulsion technology, similar mass ejection mechanisms operating at high efficiency with minimal visible exhaust. The nearly interstellar orbit isn't coincidence. It's the result of trajectory planning, a course calculated to bring it from whatever distant staging area it started from to this specific location at this specific time. Under this interpretation, C2025V1 serves a different purpose entirely. Not a control showing normal behavior, but a companion providing redundant coverage, additional observation platforms, insurance against mission failure. If 3I-ATLAS is a primary instrument package approaching on one trajectory, deploying C2025V1 on a perpendicular approach path provides comprehensive spatial coverage, different viewing angles, complementary datasets. This interpretation explains the perpendicular orbits beautifully. It explains the timing of discovery and close approaches. It explains why both objects lack prominent tails despite active comas indicating mass ejection. It requires accepting that at least two artificial objects are currently traversing our solar system. But if you've already granted that possibility for 3I-ATLAS, extending it to include C2025V1 isn't much additional speculation. The nearly interstellar orbital parameters of C2025V1, that eccentricity barely exceeding 1, could be intentional. If you wanted to deploy a probe that could later escape the solar system after completing its mission, or that could be retrieved by a mothership on an outbound trajectory, you'd give it an orbit with eccentricity close to but slightly above 1, enough energy to escape eventually but slowly, allowing time for operations in the inner system before departure. As November progressed toward the 16th, when C2025V1 would reach perihelion, observers waited to see what would happen. Would it suddenly develop the expected bright tail as solar heating intensified at closest approach? Would it undergo the brightening and coma expansion typical of Oort cloud comets, experiencing maximum thermal stress? Or would it remain stubbornly compact, defying predictions, maintaining its anomalous character right through perihelion? The answer to those questions would determine whether C2025V1 fulfills its role as a control demonstrating normal Oort cloud comet behavior, or whether it becomes additional evidence that something extraordinary is happening, something involving multiple objects with coordinated arrival times and trajectories. Think about mission architecture for a moment. If you were designing an interstellar exploration mission, sending robotic probes to survey another star system, you wouldn't send just one spacecraft. Single-point failure. Risks too much. Communication latency over interstellar distances makes real-time control impossible, so you need autonomous systems with redundancy. Multiple smaller vehicles provide better coverage than one large one. Distributed sensors can triangulate, measure parallax, observe phenomena from multiple angles simultaneously. A mothership deploying daughter probes is standard mission architecture for planetary exploration in our own solar system. Cassini dropped the Huygens probe to Titan's surface while the orbiter continued studying Saturn and its other moons from above. Mars missions regularly consist of orbiters and landers working in coordination. Extending this architecture to interstellar missions makes perfect sense. 3I-ATLAS as primary vehicle, large enough to house power systems and main sensors and communication equipment. C2025V1 as secondary platform, smaller, simpler, following a different trajectory to provide complementary observations. The perpendicular orbits mean the two objects sample different regions of the heliosphere, experience different solar wind conditions, pass through different parts of Earth's magnetosphere if that's what they're studying. They approach different planets at different times. 3I-ATLAS came close to Mars on October 3rd. C2025V1 approaches Earth on November 11th. Different targets, different data, different mission phases, all coordinated from some initial deployment event that happened months or years ago, when the trajectories were set. But proving coordination requires more than circumstantial evidence. It requires showing that the two objects are communicating, or that their trajectories were planned together, or that their behavior changes in response to each other's observations. None of that has been demonstrated. Both objects follow ballistic trajectories that could be natural. Their close approaches to planets could be coincidence rather than intentional targeting. The missing tails could result from similar but independent natural processes. The control experiment C2025V1 provides is ultimately ambiguous. It shows us that yes, another object besides 3I-ATLAS displays unusual behavior during this time period, but it doesn't definitively tell us whether that behavior is natural variation or technological signature. It narrows the range of possibilities without eliminating any completely. It makes some hypotheses more plausible and others less so, but it doesn't provide the decisive discriminator we might have hoped for. What we need is comparative data over time. If C2025V1 suddenly develops a normal tail at perihelion, the contrast with 3I-ATLAS becomes stark. That would suggest 3I-ATLAS is genuinely anomalous, while C2025V1 is just an unusual but natural comet. If C2025V1 maintains its suppressed tail through and after perihelion, staying, compact and well-behaved like 3I-ATLAS, the similarity becomes more significant. Two very different objects from different origins showing the same unusual characteristic strengthens the case for a common cause, which might be natural or technological. The observations continue, the data accumulates. Each image, each spectrum, each photometric measurement adds information to the growing database. And somewhere in that database, buried in the details of brightening curves and coma morphology and tail or lack thereof development, lies the answer to what C2025V1 actually represents. Natural control, technological companion, ambiguous middle ground that teaches us how much we still don't understand about cometary physics. December will tell us more. As both objects move through their post-perihelion phases, as they travel away from the Sun having survived maximum heating, their continued behaviour will reveal whether the similarities persist or diverge. If they both remain anomalous in parallel, the coordinated mission hypothesis gains weight. If they diverge, one acting normal and the other staying weird, it complicates any unified explanation. The control experiment we didn't ask for continues to generate data, continues to confound simple interpretations, continues to force us to question what we think we know about comets, trajectories, and whether we're truly alone in observing the events of this remarkable autumn, when cosmic forces converge. We stand at a threshold moment in human history, though most people going about their daily lives don't realize it yet. Three separate phenomena, each remarkable in isolation, have converged during these weeks of late autumn 2025. Solar maximum activity continues to bombard Earth with electromagnetic storms. Two mysterious objects traverse our inner solar system on perpendicular trajectories, both defying conventional understanding of how comets should behave. And the predicted earthquake window, that 27 to 28 day delay after intense geomagnetic disturbances, stretches ahead through early December into the weeks when 3I-ATLAS approaches closest to Earth. Let's consider what happens if the patterns hold, if the predictions come true, if December unfolds the way the accumulated evidence suggests it might. Scenario begins with earthquakes. Somewhere between December 4th and 10th, the predicted window following November's intense geomagnetic storms, significant seismic events strike in major fault zones around the world. Maybe a magnitude 7 in California's San Andreas system, perhaps a devastating 8 in the Cascadia subduction zone off the Pacific Northwest coast, possibly a catastrophic event in Japan or Indonesia or Chile, regions where tectonic plates converge with violent inevitability. The earthquakes themselves aren't unusual. These regions experience major quakes regularly throughout history. What's unusual is the timing. Multiple events, clustered within the predicted window, at locations where tectonic stress had been building toward release. Seismologists analyse the data. They note the correlation with the November solar storms, but remain cautious about attributing causation. The statistical significance is undeniable. The timing matches the 27 to 28 day delay observed in previous studies. But earthquake prediction has been the graveyard of scientific careers for decades. Nobody wants to claim publicly that space weather triggered these events. So the papers published in the aftermath carefully phrase their conclusions. Strong temporal correlation suggests potential causal mechanism. Further research needed. The language of science protecting reputations while acknowledging that something profound might be happening. Then December 19th arrives. 3I-ATLAS at its closest approach to Earth. James Webb, space telescope trained on the object. Instruments gathering light. Spectrographs dispersing infrared wavelengths. Detectors recording photons that travelled across space from this visitor from another star. The data flows down to Earth, through the Deep Space Network antennas, into computers at the Space Telescope Science Institute, where preliminary processing begins. The research team examines the spectra. They see emission lines from molecules in the jets, but the velocities are wrong, not 2 to 4 kilometers per second consistent with thermal escape from a cometary surface. 10, 15, 20 kilometers per second or higher. Doppler shifts that indicate directed exhaust at speeds only achievable through technological propulsion. The scientists check and recheck their calibrations, their data reduction pipelines, searching for errors. But the signal is robust. Multiple emission lines showing the same anomalous velocities, multiple jets showing similar characteristics. The composition analysis reveals additional anomalies. Yes, there's water vapor, carbon dioxide, carbon monoxide. But there are also ionized species, atomic emissions from highly excited states, spectral features that require temperatures far exceeding what passive solar heating can produce. The thermal mapping from MAIRI shows localized hotspots, temperature peaks at specific locations on the nucleus that can't be explained by differential sun exposure or rotation. The pattern suggests active systems, power generation, propulsion. The team faces a decision. Do they sit on the data during the proprietary period, taking months to draft papers and go through peer review before announcing anything? Or do they recognize the exceptional nature of the findings and push for immediate release? The debate happens at the highest levels: telescope directors, space agency administrators, scientific advisory panels, everyone aware that confirming 3I-ATLAS as artificial changes everything. Meanwhile, ground-based observations corroborate Webb's findings. Amateur. Astronomers capture images showing structural details, hints of geometry inconsistent with a natural nucleus. Professional observatories measure the continued lack of a substantial tail, despite clear evidence of mass ejection. The 7-jet structure persists, still oriented in multiple directions, still suggesting controlled thrust rather than passive outgassing. C2025V1, passing through its own perihelion on November 16th, also maintained its compact appearance, never developing the dramatic tail expected from an Oort cloud comet at such close solar proximity. By late December, the consensus becomes unavoidable. 3I-ATLAS is artificial. Whether still functional after billions of years of interstellar travel, or a derelict drifting through space, it's technology. An object manufactured by an intelligence that developed under another star, and C2025V1, given its similar characteristics and perfectly timed arrival, is likely related. 2 probes, 2 vehicles, 2 instruments deployed to study our solar system from complementary trajectories. The public reaction is complex. Some people feel validated, vindicated that their speculation about alien visitation was correct all along. Others feel fear, uncertainty about what such visitors might want or what their presence means for humanity's future. Still, others feel wonder, awe at the confirmation that we're not alone in the universe, that other minds exist out there among the stars. Religious communities grapple with theological implications. Philosophers debate the meaning of first contact, even if it's indirect contact with robotic probes rather than living beings. Governments convene emergency meetings. What does this mean for planetary defense, for national security, for international cooperation? If 3I-ATLAS is observing us, studying us, what is it learning? What will it report back to its makers, assuming its makers still exist somewhere? Does it have communication capabilities operating on timescales we can't detect? Are we being judged, evaluated, assessed for some purpose we can't comprehend? Scientists push for continued observation. 3I-ATLAS will pass Jupiter on March 16, 2026, coming within 54 million kilometers of the giant planet. NASA's Juno spacecraft, already orbiting Jupiter, could potentially observe the flyby with its suite of instruments, but only if reprogramming happens soon, if mission parameters get adjusted to prioritize this unexpected target over the planned science observations. The European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, already observed 3I-ATLAS in November from its position in the inner solar system. Could it observe again during the Jupiter encounter? The coordination requires resources, schedule adjustments, international cooperation at unprecedented levels. Proposals emerge for missions to intercept 3I-ATLAS, to approach close, enough for detailed imaging, maybe even to match velocity and pace the object as it exits the solar system. The engineering challenges are enormous. 3I-ATLAS is moving fast on a hyperbolic trajectory. Any spacecraft launched from Earth would need years of travel time and multiple gravity assists to achieve the required delta V for intercept. By the time we could reach it, the object might already be past Jupiter, heading into the outer solar system, becoming progressively harder to observe as solar distance increases and brightness fades. But the motivation is overwhelming. This is not just another space science mission competing for funding against dozens of other worthy projects. This is confirmation of extraterrestrial technology, physical evidence that intelligence exists or existed elsewhere in the cosmos. Every major space agency, every nation with launch capability, every research institution with relevant expertise wants to be part of the response. Money flows, projects accelerate, timelines compress from decades to years. Meanwhile, the earthquake correlation becomes impossible to dismiss. Multiple major seismic events during the predicted window, following closely after intense solar storms, exactly as the 27 to 28 day delay mechanism predicts. Additional geomagnetic storms occur in late November and December as solar maximum continues. Each one sets another timer, another prediction for earthquakes 4 weeks later. The pattern repeats. January brings more earthquakes. February continues the correlation. Statistical analysis shows probability values so extreme that even the most skeptical seismologists begin considering solar-terrestrial coupling mechanisms seriously. Research teams mobilize to understand the physics. How do geomagnetic storms induce telluric currents strong enough to influence fault stability? What role does the reverse piezoelectric effect play in stressed crustal rocks? Can we develop earthquake forecasting systems based on space weather monitoring? If we can predict elevated seismic risk windows with even modest reliability, the potential for saving lives and reducing disaster impacts is enormous. Funding agencies suddenly prioritize interdisciplinary research, bridging space physics and seismology, fields that rarely intersected before. The convergence of these phenomena, the solar storms and the artificial visitors, and the earthquake correlations, suggests something beyond coincidence. It suggests coordination, timing, intentionality. If 3I-ATLAS planned its arrival to coincide with solar maximum, if it positioned itself to observe how a planetary system responds to stellar activity stress, if it deployed secondary instruments like C2025V1 to gather complementary data from different vantage points, then we're witnessing a scientific mission. Not an invasion, not a threat, but observation, study. Data collection by explorers who travelled light years to investigate our star and its planets. What do they want to know? What questions drove them to make this journey? Perhaps they're studying solar cycles, comparing our sun's behaviour to their home star or to other stars they've visited. Perhaps they're interested in planetary magnetospheres, how different worlds respond to stellar wind and radiation. Perhaps they're examining life-bearing planets, Earth's biosphere being the primary target, with all the other observations serving as context for understanding how life develops and persists in this particular stellar environment. Or perhaps their interest is more specific, more targeted. The timing of arrival during solar maximum, the observation of Earth during periods of intense geomagnetic activity, the presence during predicted earthquake windows, all suggest focus on solar-terrestrial coupling. They want to know how stars influence planets, how electromagnetic forces bridge the gap between stellar coronas and planetary surfaces, how geological activity on tectonically active worlds responds to space weather. This is advanced science, research questions that we're only beginning to formulate ourselves, being investigated by an intelligence that mastered interstellar travel billions of years before we evolved. The implications for human science are staggering. If 3I-ATLAS is indeed studying solar-terrestrial interactions, if its observations over the coming months validate the earthquake correlation mechanism, we'll have learned something fundamental about how our planet works. Something that wasn't obvious from internal study alone, that required external perspective to recognize and confirm. In a strange way, the visitors will have taught us, not through communication or message, but through their presence as a catalyst, forcing us to examine phenomena we'd been overlooking or underestimating. But there's a darker possibility that we can't ignore. What if the solar activity itself isn't entirely natural? What if 3I-ATLAS or something associated with it can influence stellar behaviour, triggering flares and coronal mass ejections? The Sun is a massive fusion reactor, held together by gravity and powered by thermonuclear processes in its core. We assume it's untouchable, beyond any technological manipulation. But an intelligence capable of travelling between stars might have capabilities we can barely imagine. If they wanted to study planetary response to space weather, they might not wait for natural solar maximum. They might create the conditions they want to observe. This speculation ventures into territory most scientists refuse to consider publicly. Artificially triggered solar storms, controlled stellar manipulation. It sounds like science fiction, like conspiracy theory absurdity. But we're already accepting that 3I-ATLAS is artificial. We're already granting that interstellar travellers are in our solar system. Is technological capability to influence stellar activity really more implausible than the interstellar journey itself? which requires more advanced physics and engineering. We don't have evidence for artificial solar triggering. The Sun's behaviour during 2025 looks entirely natural, consistent with normal solar maximum activity. But absence of evidence isn't evidence of absence. If the capability existed and was used subtly, how would we distinguish artificial triggering from natural variation? The question nags at anyone who thinks through the implications carefully. December stretches ahead with its critical dates and predicted phenomena. Each day brings new observations, new data, new pieces of the puzzle. The accumulated weight of evidence grows heavier, the patterns become clearer, and humanity faces the profound recognition that the universe is not what we thought. We're not alone. We're being observed, and the forces at play, the connections between solar storms and geological activity and interstellar visitors, are all part of a larger system we're only beginning to comprehend. When cosmic forces converge, when solar maximum aligns with artificial visitors, aligns with predicted earthquakes, aligns with the closest approaches and best observation windows, it's no longer about individual anomalies. It's about synthesis, understanding how everything connects, recognizing the pattern that emerges when you step back and look at the whole picture rather than isolated details. The next few weeks will tell us whether this synthesis is correct, whether the predictions hold, whether the patterns are real or imagined. But the very fact that we're asking these questions, that we're considering these possibilities seriously, that we're mobilizing resources to investigate rather than dismissing the entire affair as speculative nonsense, marks a turning point. We've crossed a threshold. The conversation has changed. And regardless of what December brings, regardless of what Webb reveals or what earthquakes occur, or what trajectories the mysterious visitors follow, we're different now. We're aware that we might not be alone. We're watching the skies with new understanding. We're ready to acknowledge evidence that would have been unthinkable just months ago. The convergence continues. The forces align. The moment approaches when cosmic mysteries become confirmed realities, when speculation transforms into knowledge, when humanity finally, definitively, learns that the universe is bigger, stranger, and more wondrous than we ever imagined. 3I-ATLAS and its companion C2025V1, whatever they truly are, have given us this gift. Not answers, not yet. But questions profound enough to reshape how we understand our place in the cosmos. And in science, in the search for truth, the right questions matter more than premature answers. December will bring clarity. Until then, we watch and wonder and prepare ourselves for what comes next.